Hello there, everybody, and welcome to episode 2 of Takeo After Dark, the Winter Essentials. Welcome. We're excited to have you all with us tonight, and I hope everybody is staying reasonably warm out there and keeping your customers warm. It's been kind of a crazy week, huh? I mean, with storms going all over the place. We here in New Hampshire, we've got wind and cold, and we're going to get some snow tomorrow and Friday. But boy, oh boy, that's kind of crazy. But hey, welcome everybody. Thanks for being with us. We had 400 people, 400 and I think it was 401 register for this session. So we're really grateful. Thank you so much for choosing to spend your Wednesday evening with us. We promise we're going to make it worthwhile. Now, you're probably noticing something a little bit different this week. First, you got me. I'm John. Okay, I'm with you every week. Also with us every week is Rick. Say hi, Rick.
Hello.
The third member of this threesome is not whereas Dave was the Curly of the group, Jimmy DePalma is taking on the role of Shemp. Okay, he's replacing Curly just for tonight. Welcome, please, Jim Shemp DePalma from Wales Derby in New York, or New Jersey. I'm sorry, New York, New Jersey. It's all the same to me. Welcome, Jim. How are you, man?
Excellent. Thank you very much.
Jimmy DePalma is we go back to Wurzbo days, to 1995.
Yeah.
And despite my best efforts, Jim is achieving great levels of success in this world. Even though I've tried to help him, he's succeeding despite that. One of the best trainers in the business, and we're happy to have you with us, Jim. Jim, what if you wanted to say something to the group just about hydronics and business in general? I know I'm catching you off guard, but what would you say? What would you want? What message would you want? What's the DePalma message for the night?
The DePalma message, or the Wales Derby message that we always use, is there's no such thing as a wag. Stop wagging.
Yep.
Do the math. Make money.
Yeah.
Plain and simple. If I do the math, I stand a much better chance of making money. If I wag it, I'm gonna get bit in the ass.
Yep.
Yeah.
Or not
you
get
guess
the job.
Right. When you guess, one of three things can happen, and two of them aren't good.
That's correct. That's correct.
All right. Excellent. And also off in the wings, we have Tim Ward and John Messenbrink from our sponsors, Mechanical Hub. Say hi, everybody.
Hey everyone. Hello, everyone. Glad you could make it to session 2. John was
Eloquent
a little
gentleman as always.
we were kind of in the ether there.
Oh, there you go. Hey, what's going on in Mechanical Hub this week, guys?
Well,
Podcast.
Yeah, podcast. I tried to get Eric to come on tonight. He might make a special appearance. I'm not sure.
Hold the phone, people. Wow. Hold the phone.
We'll see.
An Eric Ani appearance. This is unprecedented. I got to check the news. I think what just froze over.
Yeah. Well, he's busy with no heat calls, so.
Well, of course he is. He actually, unlike the rest of us, he actually works for a living. God bless him. And good. I hope he does. I haven't talked to Eric in quite a while. And one of the things I love about Eric is he's got a sense of humor that's almost as twisted as mine. And in some certain ways, I think he takes it to different places. And he's a lot of fun. Anyway, enough of the
real quick. John,
go ahead, guys. Say again.
If anyone hasn't signed up for our newsletter, we have a feature from. I did a Q&A with Mark Chaffee. So it's kind of a forecast of 2021 and what Takeo's doing in 2021 and kind of navigating through the COVID crisis and all sorts of good stuff. So check that out.
Yeah.
Excellent. Very good. Always good reading. And you guys, like I said, you guys do just terrific work, and we really appreciate everything you do. Alrighty, let's get this show on the road. Takeo After Dark, the Winter Essentials. Okay, and tonight is episode 2, and of course, you know our spirit animal, the great Bruce Campbell, our actor, who somehow Dave Holdor figured out a way to put Bruce Campbell's head on Bernie Sanders' body. I don't know how he did it, but he did it, and that's why he's curly.
It should be bobbling. It would be even
It should
better
be.
if like moving back and forth,
Oh yes, and if you could get the jaw to move and talk, it'd be serious South Park action right there. So tonight our topic is pump curve essentials. Pump curve essentials, and we're going to break that down. We're going to break that down for you in ways that hopefully it will make sense to you, and hopefully it'll make a difference to you in how you go about selecting circulators, even a small little wet rotor circulator. The pump curve does make a difference.
Absolutely.
Now, sorry, just hit my microphone. Before we get rolling, I want to go over real quickly just the control panel. So if this is your first time, so you know how to use it, do me a favor, just take a gander at this thing right here. Okay, that's your little arrow. If it's pointing to your right, that's good. That means your thing is expanded. Your control panel is expanded. If it isn't, if it's to the left, just click on it and that control panel will expand, and that's how you can make things work. Of course, up on top, you've got your audio selection. You can confirm your speakers, etc. So you know it. So if you can't hear me, you don't know what the heck I'm doing. So, but that's how to control your audio. Handouts, we don't have any tonight, but we will in future episodes. Your handouts will be found right there, okay, where it says handouts, and you just click on it and download it.
John.
And then the most important part is questions, all right? If you go to the question section, that's where you're going to type in questions. So if everybody could do a hi, hello, how are you for me right now, that way I know you know how to use it and I know you can hear me. And
they're actually coming in. They're coming in.
Dog.
Yeah.
Here we go. Got all the highs. Hi, hello, how are you? Very good. Excellent. Tracy's with us. Jim.
Beauty.
All right. Excellent. Good, good, good. Mr. Eisenhower's with us. Terry, Jim Picard. Boy, look at everybody. Excellent. Now, tonight we will also, like we did last week, we will be giving away a bunch of cool prizes. We are going to have 5 of you will win a Takeo After Dark t-shirt and mask, and Takeo mask. And 1 of you will win a t-shirt, mask, and a wicked groovy prize package that will include a mug. It'll include a little Bluetooth thing. I mean, there's all kinds of whatever Holdorf has in his garage that says Takeo on it, he'll send it to you. So what the way you're going to get noticed is interact. Okay, ask questions, be involved, and we will be monitoring that and picking everything out from there. And we have someone from Yuma, Arizona. How you doing, Albert? From Yuma, Arizona, where it's actually warm. How about that? All right. But the 310 to Yuma, one of my favorite movies of the last 10 years, too, by the way. Not that that has anything to do with it. Maybe we'll do a 310 to Yuma theme at some point. All righty. If you're on a phone or tablet, last thing, phone or tablet, there's your control panel down at the bottom. You've got your webcam and presentation screen down at the bottom. You have where you can toggle back and forth between your webcam and the presentation. Audio settings are there. The attendees is not enabled, but if you're going to ask questions, that's down there on the bottom of your phone as well. So if you need that. Excellent, excellent, excellent. Okay. Shall we get to work, boys?
Yeah, let's do it.
All right. And ladies and gentlemen, now we got Green Bay, Wisconsin. Peggy from Greenway, Wisconsin is here. We got a Vancouver, British Columbia.
BC.
We got Ontario. All right, God, we're representing from all over. I love it. Thank you guys so much. All righty. So if I had known Eric was going to be here, I would have made sure that he saw this, but we're just going to do, whoops, hold on. There we go. We're going to do this for Eric real quick. There we go. That didn't come out right. Anyway, pump curve essentials, episode 2. We're going to talk about pump curves. What do they mean and why do they exist? First off, I want you to think here, people. This is kind of echoing what Jimmy had to say earlier about doing the math and doing it right. What is it that what ultimately do we care about? If all we care about is this, either they have heat or they don't have heat. If that's the only thing we care about, is that nobody out there is freezing to death and blaming me. All right. If that's the only hurdle you care to cross, well, congratulations. To me, that is the equivalent of getting a D-. All right. You passed. Barely. You did the bare minimum to meet the bare minimum requirements. All right. That's all you've done. You haven't excelled. You haven't done anything extraordinary. You haven't even done something that was average. You're simply not, people aren't freezing to death. And a lot of times that's all I hear from guys. They say, hey, it works. It works. Well, what do you mean it works? Well, hey, nobody's freezing to death and blaming me, so it works, right? Well, again, that's a D-. Professionals, as we know, aspire to more. They aspire for higher performance, higher solutions, greater comfort, maximum efficiency. It's not enough just to have people not freezing to death. What they want is the equipment and the system that they install to perform to its peak efficiency for a maximum life cycle and maximum performance. That means understanding how different things work. Okay, that means understanding that circulators matter. It means understanding that how you pipe up the boiler matters. It means understanding how you choose to zone a system matters. All of this stuff is important, okay? Understanding pump curves might be the single most underappreciated skill in our business. Understanding what these pump curves mean and how to interpret them and how to apply pump curves properly will go so much farther in making sure your systems work efficiently, effectively, comfortably, and for the long haul than practically anything else you can do. Understanding pump curves, gang, is basically it basically amounts to the difference between installing a system or just a collection of parts. I've said this many times before, is anybody can install a bunch of parts, right? You can throw a boiler in there, some pipes, some valves, fittings, some pumps, some heat emitters, put it all together, wire it up, keep the water on the inside, light it on fire, and keep people from freezing to death. That's not a particularly difficult trick, okay? That's not that hard to do. A reasonably competent handyman could pull that off. Not a highly skilled one, a reasonably competent one could do it, and he could do it for a heck of a lot less expensive than you could. So if we understand that D- isn't that hard to achieve, we now have to understand as professionals, how do we separate ourselves from them? It's not enough to say we're professional. It's not enough to say I do quality work. It's understanding that the parts and pieces you choose matter and they impact how the system performs, particularly the circulators. So understanding pump curves, gang, is tantamount to understanding the difference between what makes up a system versus just installing a bunch of parts. Anybody can do a bunch of parts. It takes a professional to understand a system and understand how these things work together. That's the difference, and that's the importance of pump curves. All right. How are we doing out there, folks? Is pace okay and everything? Just give me a little bit of feedback in your section there, and if you could just let me know. Okay, very good, very good.
All good.
All right, excellent, excellent. Well, what we're going to do now is just I want to tell you first, where do pump curves come from? Everybody's seen a pump performance curve chart, right? It's you got a little chart, and on the x-axis down the bottom you have gallons per minute, and the y-axis you have total head in feet. Now, total head in feet isn't feet of height. It's simply a way we in the heating business interpret pressure differential or pressure loss or friction loss in piping. Pressure differential on a gauge is going to be read in PSI. To convert PSI to feet of head, you simply multiply your PSI times 2.31. Where does that come from? Well, a column of water 28 inches high or 2.31 feet high will have a gauge pressure down at the bottom of 1 PSI. Okay, so that has to do with the height part. In terms of pressure differential, 1 PSI worth of friction loss or 1 PSI worth of pressure differential, okay, is going to be equal to 2.31 feet of head loss, okay? So that's what the head loss part means, and that's how we arrive at it. Now, how do we come up with a pump performance curve? Well, we use a little contraption like we have on the left here, this big old vat of water, all right, with a standpipe coming out of it going to a circulator. On the outlet side of the circulator, there's a pressure gauge and a flow control valve, okay, to determine the gallons per minute. So what we do first, the first step is to close that flow control valve completely. So the valve itself is completely closed, and then we turn the pump on. What's the flow rate at that point? Well, it's a big fat 0. There's no flow, but that pressure gauge at that point should go bing. It should be pinned, right? It should be the highest it's ever going to read. All right, so we read the pressure on that, multiply it by 2.31, okay, and then we plot it on that curve at 0 gallons per minute, okay, at 0 gallons per minute. Then we open up the valve to say a half a gallon a minute or 1 gallon a minute, and then we read the pressure. And then we do it again to a gallon and a half, 2, 2.5, 3, continuing on and on and on, and reading the pressure. Now, as we open up that valve, the pressure should drop a little bit. Open it up to another flow rate. The more flow, the more the pressure on that gauge is going to drop. So once we have all those numbers, we plot them out on the chart like so. Okay, we plot them out on the chart, you know, with the old XY thing. Remember you did charts and graphs in like 5th grade and 6th grade, and you thought it was a complete waste of your time, right? Complete crap. And I'm never going to use this in the real world, man. Well, today's the day, right? Now you are. That's right, baby. Now, once we have all of those points on the plot, we just connect the dots, and there's your performance curve. All right, that's where the pump performance curve comes from. And we call it a performance curve because this is what the circulator will do. The circulator will give you a combination of flow and head, okay? A combination of flow and head pressure differential somewhere along that line. It'll be somewhere along that line. It has to. Energy in equals energy out. The circulator has to perform somewhere on that line. Now, that's part one. Part two is now we introduce another curve, and I'm not going to show you the math behind this. I'm going to show you an easy way to figure it out. But once we have the pump performance curve, now we have to find something called the system curve. But before I go back to the system curves, I just want to go right here. And we have flow and head. We have flow and head. And how that circulator works on that curve is going to depend on a lot of things, okay? It's going to depend upon the horsepower of the motor. It's going to depend upon the speed at which that motor makes the impeller go round and round. And most importantly, in our little wet rotor circulators, it's going to depend upon the impeller itself, specifically the size and the shape, because the impeller really matters in what a circulator can do, okay? So what we have here is an artist's rendition of an impeller. All right, it's a closed vaned impeller, meaning there's plastic on both sides, and we have these vanes on the inside. We have the eye of the impeller, and that's where the water enters enters the impeller while it's spinning. And while it's spinning, those vanes will fling the water from the inside out in a 360-degree pattern. That water will then go through a narrowing passageway on the discharge side of the circulator that's going to change the velocity that's being added by the impeller to pressure, and it creates a pressure differential. You want a good description for a circulator is it's a pressure differential machine, okay? Now, we're concerned about two different aspects of the impeller, okay? We're concerned about two different aspects. We're concerned about the thickness of the impeller, as well as the diameter of the impeller, how big across it is, okay? How thick it is and how big across it is. Why? Well, because if I have a circulator running at a specific speed, at a specific RPM, okay, if I have a thicker impeller, all right, that circulator will move more gallons per minute than if I had a thinner impeller in that same circulator going at that same RPM. So the thicker the impeller, think of it this way, the thicker the impeller, the more room there is for water in there, the more, and that's all spinning, the more gallons per minute it can move, right? Does that make sense? So the thicker the impeller, the more GPM a circulator can move. Now, diameter is another aspect of it. The bigger the diameter, okay, the bigger the diameter, or the wider the impeller is across, the longer the fling, okay, when that water enters the impeller and we fling it from inside to out, the wider the impeller, the longer the fling, the more head pressure differential that circulator could create, as opposed to an impeller that's not as wide across running at the same RPM. All right, does that make sense? So the thicker the impeller, the more GPM, the wider the impeller, the more head pressure differential, okay? And why do we have different impellers? Because we have circulators that have different performance curves. You're looking at two impellers right here. This is a 007 impeller on the right. That's an open vaned impeller. It's not very big around, but it's wicked thick, okay? Over here, we have a 008 impeller. You see that as a closed vaned impeller. It's not as thick, but it's bigger around. All right, it's not as thick, but it's bigger around. By the powers of deduction, based on what we've just learned, we can say that the 007, being an impeller that is thick but not that big around, will tend to be a high flow, relatively speaking, low head pressure differential pump performance curve. All right,
That's right.
what we would call a flat curve, and we'll show you what that looks like in a second. The 008, on the other hand, being bigger around and thinner, if it's running at the same RPM, is going to have a lower flow, higher head performance curve. Same horsepower motor, same RPM, two different performance characteristics. And why? Because they're for two different jobs. Okay, even a little 125th horsepower circulator has two different jobs. We give you two different performance curves, two different applications, two different circulators. How are we doing out there for questions, guys?
No, we just had one talking about the actual speed, and you already nailed it. If we have I mean, is the speed going to remain constant if you go to a bigger impeller? Yes, if that motor has a certain RPM, it's going to run at that RPM. Now the performance is going to be different, but
Right.
At that same RPM, or let's just call it speed, at that same speed, it's going to have a different performance.
Right, and the difference is more than just in the impeller. The impeller is the key difference. The volute, Bob, will be machined a little bit differently to accept the impeller. So
Yep.
you can't like take a 007, pull out the motor, pull out the cartridge, put in a 008 cartridge and try and jam it back in. It won't fit physically. They're milled differently and cast differently.
I bet if we asked Jimmy, he'd say somebody's tried that.
Somebody's tried it. You get a big enough hammer, almost anything can happen, right, Jim?
Amen.
But
Yes.
we've all seen it, right? Yeah. So there's a difference. It's interesting. The 008 and the 007 have the exact same motor, the horsepower motor. It's a 125th horsepower motor. It's the same motor. Okay. The impeller's different and the volute's different, just so it'll fit, but they go at the same RPM. Just different shaped impellers give you different performance curves. And here's kind of and why do we have those? Why do we have different times of impellers? Okay.
Hey, John.
Yeah.
George Easton's he's saying, can you give us an example? And he's got but I think maybe that's where you're going right now. I'm not sure, George, do you want an example of the different performance curves, or do you want an example of why? I think clarify that, I guess.
Okay. Yeah. We're going to go over right now the difference in applications, if you will.
Okay.
I'm seeing another couple of questions. The same horsepower will work, but at the same speed, but different types of output, different performance curves. Like I said, the thinner, bigger around impeller will be a lower flow but higher head pressure differential. It'll be a steeper type of curve, whereas the 007 is higher flow, lower head, flatter type of performance curves. I got a picture coming up in just a couple slides here, Bob, that I hope will clear that up for you. Okay, how is it affected by pipe size? Good question, Mario. First off, not at all. Pipe size is going to determine is going to determine the system curve, which is what we're going to be talking about next. The pipe size and the system itself, that's going to determine the system curve. It's not going to determine whether a specific pump performs like a flat or a steep curve pump. That's going to be fixed. A steep curve pump is going to be a steep curve pump. Pipe size and the system you connect it to is going to determine where on that pump curve it works. All right. So we're getting a little ahead of ourselves, but I'll try and catch up with you guys because I think you guys are getting it. We're working towards it.
John.
Now, yeah, go ahead.
Cecilia is asking about the impellers themselves. Is it a plastic impeller? Are we doing that because they're easier to produce, probably less money, that sort of thing? The other reason, or is there another reason, is the question. I'll take a stab at that one. From the standpoint of the material that the impeller is made of, has to do with how long will it last in that particular application. There's a couple different materials that we use depending on what that unit's used for. If it's going to be used for potable water, we have to use a particular product that is NSF listed and approved for that application. Another type of plastic might be used when we're just doing closed loop heating or cooling applications. So hopefully that answered that question. Go ahead, John.
Right, and I think a lot of it also is for the smaller circulators. It is cost, it's availability, et cetera, and that type of material is perfectly acceptable for that applications. We make larger circulators up to, pumps up to 250, 350 horsepower that will have bronze impellers that can be trimmed and milled to match the specific application. So it's just a matter of size at that point. All righty then. So let's take a look at this. Over in Europe, why do we have different ones? What's different types of jobs, different types of applications? European systems, what we have are, you have home run type systems like you see here, where each radiator will have its own supply and a return from a manifold, all right, from a centralized manifold. And it's usually fairly small diameter pipe. Either 14 millimeter in many cases, where you got a 14 millimeter supply and a 14 millimeter return going from a manifold to a panel type of radiator. And the control strategy is one of these things, a modulating thermostatic radiator valve. It's the thing that controls the temperature and the comfort level in each individual room, which always seemed a little screwy to me, because the thing that monitors and controls the comfort level in each room is about 1 3/4 inches away from the hottest frickin' thing in the room. But hey, what do I know? I'm not European. But that's kind of how they work, and they modulate. They open, they close, they're opening, they're closing. It's not like a zone valve that's either open or closed. These things are in varying degrees of openness or closedness, if you will. Generally speaking, those circulators will run 24/7 simply because they don't have thermostats over there. It's just the way they do things. Not that it's better or worse, it's just plain different, okay? And they'll use very small pipe, and they will design to very wide delta T's, typically upwards of 40 degrees, okay? The water might go out at 150 and come back at 110, all right? So if we understand about how we figure out flow rates, you're gonna start to understand why European type circulators tend to be lower flow and higher head. Okay, it's because simply if I've got if I got a house that has 80,000 BTUs, which is a ridiculously large house, okay, and I design to a delta T of 20 degrees like we do here, okay, GPM equals BTUH divided by delta T times 500, right? That's the universal hydronics formula. 80,000 BTUs divided by 20 times 500, or 10,000, that's going to give me a required flow rate of 8 gallons per minute. If that same system designed like this with little pipe was designed to a 40 degree delta T, so now it's 80,000 divided by 40 times 500, or 20,000, I'm delivering the same 80,000 BTUs, but I'm doing it with 4 gallons a minute. All right, 4 gallons a minute, a lower flow rate. I'm also going to have a lower overall flow rate for the circulator and a lower flow rate to each individual radiator. Now, again, I'm running 14 millimeter pipe to each individual radiator. That's a little smaller than 3/8 inch pipe. That size pipe to each individual radiator, even at those low reduced flow rates, there's going to be significant pressure loss. So what we're seeing with European style systems, we have systems that require, relatively speaking, lower flow rates, but relatively speaking, higher head requirements, higher head loss requirements. So we wind up with a circulator. Typical European circulators are going to be designed specifically for that application with low flow, high head.
Hey, John.
Now here in North America, yes, sir.
Let's do a quick check. You folks send us. There's a couple of individuals said they couldn't hear. Let's just make sure it's just a couple. And so just real quick, give us a heads up that you can hear what John's saying right now. There's a yes, 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 yes. Okay, so you folks that are sending in things saying that you can't hear, sometimes
can't really
log
tell
off.
them anything, Rick.
Okay.
Yeah, you might have to send them a note.
It's
I will.
You
probably
can't hear me, raise your hand. Right?
That's good. Okay.
I was just teeing that
Well,
one up. Sorry.
continue. I did. I gave it to you. You took it and ran with it. So
Okay, let's continue. Let us continue. All right, yeah. If you want to send Georgia, I think it was, or is that Rodney? If you want to send Rod, I saw that. If you
I
want to send
will.
Rodney a little note in this section that
I'll
just
do it.
he may have to log out and log
Sorry
back in
about that.
again.
That was beautiful. Take me a while to live that one.
Yeah, no, you think we're going to let you forget it? No. All right, now over here, we got a little bit of everything, man, right? We got fin tube baseboard in series loops. We got radiant floor heating with manifold actuators, which is kind of like a zone valve system. We zone pump, we zone valve. We have unit heaters, we have air handlers, we got this, that, and the other thing. And a lot of times we have all those in the same house, right? We have them all in the same house. So we got to put this together and try to make some kind of generalizations. And the one generalization we can make is we have multiple zones. We will have a lot of on-off zones, whether we zone pump or whether we use zone valves. We'll have zones with thermostats. And we do something really kooky, crazy, and nutso over here. When we have enough heat, we turn stuff off. I know, crazy, right? If there's enough heat in a zone, we'll close a zone valve. And if we don't need any more heat in the house, we'll go one step crazier. We'll shut the pump off. I know, crazy, right? But that's what we do. It makes perfectly good sense to me. You know, why would you, if you were mowing the lawn, all right, if you mowed the lawn and you finished mowing the lawn, would you just put the lawnmower in the garage and let it run until the next time you wanted to mow the lawn? No, that's nuts, right? Shut it off. You shut it off. To me, the most efficient circulator, we talk a lot about circulator efficiency. The most efficient circulator is the one that's off because it doesn't use any juice then. It's simple, you know, it's simple. And we're talking about fractional horsepower circulators. There may be a case to be made for a 300 horsepower circulator and the starting torque that thing needs to let it run. That's a different conversation. You're talking about your house, my house, our house. It's a 125th horsepower circulator. Shut it off. All right, shut it off. It's not going to hurt anything. All right. We also use, when we design around either a 20-degree delta T for most residential hydronics, indirects are generally designed to a 30-degree delta T, or when we do residential radiant, which might in fact be designed to a 10-degree delta T, what we're dealing with here are smaller delta Ts and larger pipe. All right, larger pipe. So smaller delta Ts will generally give you a higher flow rate. Larger pipe will generally give you lower head loss. So we got high flow, low head versus low flow, high head. And what we wind up with, curves that look like this. Steep curve, okay, steep curve, lower flow, higher head. Flat curve, higher flow, lower head. In the pump manufacturing world, steep curve pumps like we show here, and it's all relative to one another, okay? Steep curve pumps are typically called a European style curve, where a flat curve is typically called an American style curve in the pump manufacturing world, because that's traditionally what we've seen installed, okay? And it all has to do with habits. It has to do with how we've traditionally installed systems and designing circulators for the specific application. You know, I've asked guys, you know, why do you have why would you have a steep curve pump? Why would you, you know, put in a steep curve pump or a high head pump? And I had one guy said, well, they're hydraulically more efficient. I said, well, where did you hear that? He goes, well, that's what the sales guy told me. Well, where did he hear that? I don't know. It's nonsense. It doesn't really apply, but people understand, you know, they give you reasons for certain things that may or may not be true. In terms of hydraulic efficiency, steep curve, flat curve doesn't really make a whole lot of difference. It's what's the application that we're looking at. We're going to go over some applications here in just a second. The other part of this, all right, the other part of this that makes knowing the difference between a steep curve pump and a flat curve pump is a totally different curve called the system curve. All right, the pump curve we come up with in the lab when we design these things. The system curve is truly unique to each and every piping system out there. It's a hydraulic fingerprint. Okay, it's an identifier of flow and head. Okay, it's as unique as a fingerprint for each individual piping system that you have. Okay, in this case, let's say I do some math here and I find that I need a circulator that can do 3 gallons a minute at 7 feet ahead. Just give me just a number. 3 gallons a minute at 7 feet ahead. This is my requirement right here, okay? 3 gallons a minute at 7 feet ahead. And if I do some math, all right, there is a mathematical relationship between flow and head, okay? As flow goes up, head goes up exponentially. As flow goes down, head goes down exponentially. It's not really a straight line. It's kind of a curved line like you see. And there's a mathematical formula to figure it out. I'm not going to bore you with it. I'm going to show you an easy way to do it. But it's the same. We kind of go through the same process as you go through when we did the pump curve. You figure out the flow and head at different points. Okay, so we got a point here. We have a point here. So it's a dot, another one there, another one here, another one here. When we get all these dots, we just connect them, and there's the system curve. Why is the system curve important? Because it's all about the intersection right there. It's all about the intersection, because the intersection of the system curve and the pump curve is where the system's going to operate, okay? It's the operating point. That's what we're going to do, all right? That's what we're going to do. I may need 3 gallons a minute at 7 foot ahead, but once I slap this particular circulator on it, that specific circulator, I'm going to get 6 gallons a minute at maybe 11 feet ahead. Depending upon where we're at, we're definitely over pumping. That's going to have implications. And depending upon the kind of system, that head pressure differential might also have implications in system operation. All right, so that's kind of where we're at here. But that's the importance. It's all about the intersection. It's all about the intersection, because that's where the system really, really works. Okay, that's where it really works. I told you I'd show you an easier way to plot a system curve. I'm not going to do the math, because the math is like head 1 divided by head 2 times. I can't. That makes my hair fall out, as you can see. This is a Bell and Gossett system sizer wheel, which may be one of the most useful things you can pick up in this world. The B&G system sizer wheel. If we go to the back side of it and scale 5 allows us to figure out the points on a plot on a system curve. All you have to do, the white window is gallons per minute, okay? And these numbers up here is feet of head. Okay, it's feet ahead. Ignore CV for a minute, because we don't use it in this instance. Okay, so let's say my system, I have a system, different example, 3 gallons a minute requires 3 gallons a minute at 6 feet ahead. So what I'll do is I'll line up the 3 to the 6, and then I can go in either direction and figure out the feet ahead at different flow rates. So if I wanted to go this way, I'd say at 2 gallons a minute, what's my feet ahead? If I was running 2 gallons a minute through that piping system, what would the head loss be? In this case, the head loss looks like it would be almost 2 3/4 feet ahead. Okay, cool. Let's go up to 4 gallons a minute. 4 gallons a minute, my head loss is going to be 11 feet ahead. Let's go to 5 gallons a minute. At 5 gallons a minute, I'm at 17 feet ahead. At 6 gallons a minute, I'm at 24 feet ahead. And at 7 gallons a minute, it looks like I'm at about 33 feet ahead. Okay, as flow goes up, head goes up exponentially. Head goes up exponentially. Why do we care? Again, we want to plot out that system curve on our pump performance curve chart. So let's take a look at this. How would that look? Here, these are 2 of our 00 3-speed circulators. Okay, the small one here is the 0015, and the larger one here is the 0013. It's a bigger pump. Even though it's a lower number, it's a bigger pump. So let's take a look. First off, we had 3 gallons a minute at 6 feet ahead, right? That was our first point. But let's put these other plots on the chart, and then let's connect them. All right, and what you'll see, this is kind of where we're going to intersect. So this is where I want to be, right? Right there. If I set this to low speed, low would be perfect, wouldn't it? Low would be perfect. That's a little over 3 gallons a minute at about 7 feet ahead. It doesn't get a lot better than that. When you're talking about a fixed speed pump that isn't really a Delta T pump, that's as good as you're going to size a pump in my book right there. But where do these, everybody who's seen a 3-speed circulator installed, you know this. Where are those things always set? Where are they set? They're set in contractor no callback mode, the highest speed it could possibly go. All right, whoops, the highest speed it could possibly go. So in this case, we're looking right here. Again, my line's a little goofy, but we're looking right there at about 30 3/4 gallons per minute. Now I need, okay, I'm sorry, 4 3/4. Excuse me, that's 4 3/4 gallon per minute, right about there, 4 3/4 gallons per minute. I need 3, but I'm giving it 4 3/4. Am I going to get heat? Yep. Is anybody going to freeze to death and blame me? Nope. Okay, none of that's going to happen. So the system is going to quote unquote work. However, the math doesn't lie. Like Jimmy said earlier, the math, do the math, do the math. The math doesn't lie to you. Again, we talked about the universal hydronics formula just a second ago. GPM equals BTUH divided by the product of delta T times 500. Now, remember math class again when you were doing algebra and you're thinking to yourself, I'm never going to use this crap ever in the real world. Man, I'm never going to use it. Why am I wasting my time? I don't need this stuff. This is a waste of time. Well, today's the day. Okay, this is an algebraic formula, and if we understand algebra, we can isolate for anything and solve for anything. So here we're going to manipulate a little bit and solve for delta T. Delta T equals the BTUH I need to deliver by the GPM I'm using to deliver it, divided by the constant of 500 for 100% water. Okay, so BTUH in this case was 3 gallons a minute. It was 30,000 BTUs. That was the load, 30,000 BTUs. But I'm not delivering it with 3 gallons a minute. I'm delivering it with 4 3/4 gallons a minute. So 30,000 divided by 4 3/4 divided by 500. The best delta T I'm going to see in this system, boys and girls, is about 12 and a half. 12 and a half, and that's on the coldest day of the year. And that's the only time I'm going to see 12 and a half, provided I haven't oversized everything else. All right. Most of the heating season, I'm going to have a delta T in single digits. And in fact, most of the heating season, I'll bet you $50, I'm going to have a delta T of less than 5. Less than 5. I don't care whether it's a cast iron boiler or a modulating condensing boiler, you are short cycling. Okay, and that kills efficiency, that kills components, that kills systems. Okay, this is the inside baseball here of hydronics, in my opinion. Understanding that correlation between system curve and pump curve, and understanding that pump curves matter. Okay, that is the thing that's going to determine how efficiently your systems will operate. I'm not talking about combustion efficiency and doing a combustion analysis. That's important. That gives you certain numbers, but don't mistake that little percentage that it's giving you there for the system-wide efficiency. If that's burning efficiently, but it's short cycling like crazy, all right, you're not doing your customer any favors at all, okay? Any favors at all. All right, how are we doing on questions out there, gang?
Looking good so far.
All right, I see a lot of stuff coming up here. This is good stuff. This is good stuff. All right.
People clarifying, understanding that whole resistance, it's particular to the system. That's why we call it a system curve. What size pipes, not just the pipe, it's the valves, it's the fittings, it's the heat exchanger, it's the air separator, the dirt mag, all that other stuff will impact that. So that's why it's so unique. So not just
I see that one. Doesn't the system curve depend on pipe size? Absolutely.
Sure.
That's what determines your head loss. Yeah, absolutely. Because you think based on the pipe size and based on everything else, we came up with 3 gallons a minute at 6 feet ahead, right? That's how that worked. And that's based on a 20-degree delta T, presuming a 20-degree delta T. Now, 30,000 BTUs is the load, right? It doesn't matter. I've heard guys say, trainers say, well, if you're putting more gallons per minute, you'll get a little bit more output from that radiator. I said, well, whoopee, who cares, right? You don't need more output. You get all the output. You only need 30,000 BTUs, 3 to 4% of the heating season at most. So who the heck cares if you can get more out of it? You don't need more. You need what you need, right? You just need what you need. So,
Couple
go ahead.
couple clarifications here. Jessica, can you explain the delta T bit more? Low delta T, you're not getting all the heat possible from the system? Go ahead and clarify that, what Jessica's asking. Yeah.
Yeah, it doesn't mean that you're not getting all the heat possible. It simply means you're delivering the heat less efficiently. Okay, because remember, GPM equals BTUH divided by delta T times 500, right? So that delta T, when we design for a delta T, we design for a specific targeted delta T, 20 degrees. Why did the industry settle on 20 degrees? And I'll tell you why the industry settled on 20 degrees, because 20 times 500 is 10,000, and you can divide anything by 10,000. It did make the math,
yeah,
right? But that doesn't mean 20 is not a desirable target, okay? Because think about this: if the water goes out at 180 and comes back at 160, the boiler has to work to bring that water up from 160 back up to 180, right?
Correct.
Okay. It has to replace the heat that is lost, okay? And that's a nice long run time. If we had a 10-degree delta T, if we oversized the pump and the water was going out at 180 and coming back at 170, now the boiler has to bring the water up from 170 to 180. Only a 10-degree temperature rise. It's going to cycle shorter and ultimately more, okay? What we're really after with any boiler is fewer cycles that are longer. We'd rather have fewer longer cycles rather than more short cycles, okay? Because short cycles wear out components, okay? They're designed to last. It's like a light switch, okay? You can just turn a light switch on and off, on and off, on and off. You'll eventually wear it out, right? Same thing with that, all of the moving parts in the system. We want to give them minimal cycles, but maximum on time for overall enhanced efficiency. So we stay above the steady state efficiency line and maximize our burn efficiency for as much time as we possibly can. I don't know if that helped answer your question, but I had fun doing it. So I hope that answered your question.
John, somebody mentioned that, most people don't care about short cycling. Maybe as the contractor you don't, but your homeowner is, because just as you explained, it's going to cost them a fortune.
Yep.
Right. Right. When you short cycle
bill, I had a $500 bill for 1,500 square foot living space one month because the system I had. Yeah, yikes. That was the point of too much pain, and we had to make a change. And things were oversized and short cycling like crazy. It hurts.
Maybe the best example to bring it home is highway driving versus stop and go city driving, but with a twist. Okay, highway driving, you're driving down the highway and you're going 60 miles an hour or 70 miles an hour, a nice steady speed, okay, for a nice long time, and your miles per gallon is nice and high. Compare that to stop and go city driving, but with a twist. The twist is you're sitting at a stoplight, red light, and you have the car in park and the engine off, okay? Then when the light turns green, you start the engine up, you put your gas to the floor, throw it in the park, and screech on down the street until you see another red light. You don't take your foot off the gas, you jam the brake on, come to a screeching halt, throw it into park, and shut the engine off, and wait until the light turns green so you can do it all again. That's the difference in terms of how efficiently the thing works, I guess, if that helps. But that's it's always it's helped how I look at it anyway. And Jim makes a very interesting point here about a delta T and how it kills condensing boiler efficiency. Yeah, if you're not bringing the water back to that boiler as low as you possibly can, you're reducing that boiler's ability to condense. And if it's not condensing like it should, it's not going to be as efficient like it should, and your customer's not really getting what they paid for. Okay, so I think that's kind of that's another way of looking at it, I guess. All right. Does your delta T pump take care of this issue? To a degree, yes. It does have a minimum speed, but it's a fairly low minimum speed. the bigger the system, the more it takes care of it. As a zone pump for small zones, what you're going to find is more often than not, you have a fixed speed 9-watt pump, all right, which isn't a bad thing. It's certainly not a bad thing, but it is what it is. I know, let the dog out. I can't get through a webinar, day, night, doesn't matter. I cannot get through a webinar without my little guys barking. That's just the way it is. Alrighty, let's continue. Modulating burners, do they play into the discussion? Wouldn't they have longer run times at a lower output setting? Again, potentially, but that still has to do with how high they have to bring the water temperature up and how small the load is compared to the zone. Because now we're getting into a different discussion now about microzones. If you have a lot of little zones and your smaller zones have a smaller load than the lowest firing rate of the boiler, you're going to short cycle there too. Okay, so it's all part of the package. And then another thing about modulating burners still has to have water going through it. So you really have to size the boiler pump appropriately. And Rick does a wonderful presentation on sizing boiler pumps. If you oversize that pump, I don't care if the boiler modulates or not, it's going to short cycle like crazy. It doesn't matter. Okay. So yeah, it depends on the turn down ratio. But again, if you got, I've seen boilers with, 10-to-1 turn down ratios, and we still have a couple of small little zones that are smaller than that. Turn down ratios are wonderful things, absolutely. But there's no one answer that eliminates your concern for all the other stuff, right? It's a system. It's a system. So you think about the turn down ratio. You think about buffer tanks if you have a lot of small zones. You think about sizing your boiler circulator appropriately to a nice wide delta T, and make sure that pump is small enough, not that it's big enough, make sure that it's small enough. And then you watch your delta T over on your system side, and bang, now you're starting to talk about putting together a system as opposed to a collection of parts. Cool. All right, this is fun, guys. This is fun.
Lots of stuff coming in. Lots of questions.
Yeah, I'm having a good time. Let's talk about zone valve systems.
I can tell.
Whoa, say what?
I said I can tell.
Hell yeah. All righty, let's talk about a zone valve system real quickly, a zone valve system. And this is a 3-zone zone valve system. And when you have zone valves, you have multiple system curves. You'll have one system curve for every possible combination of zones that could be firing at any given point in time. For example, a 3-zone zone valve system will have 7 system curves. All right, let's count them out. Zone 1 by itself, zone 2 by itself, zone 3 by itself. Zone 1 and 2, zones 1 and 3, zones 2 and 3, and zones 1, 2, and 3. That's 7 different system curves. 7 different system curves. So you have 7 different points of intersection on a pump curve. So I get 7 different system curves. And if we add the pump curve now, let's go ahead to the next one. We add the circulator. Now we have 7 different points of intersection along that pump performance curve. Now, what you're looking at here is a 007. I saw someone say earlier, 007 seems like it's too big for a lot of applications. Why is it on everything? Well, it's one of those circulators that its curve fits so many applications.
Yep.
Okay, it fits so many applications. And you have to understand this stuff that we're really getting into now. The only reason we can get into it now is because we have tools, i.e. variable speed circulators, that allow us to address this overpumping issue to varying degrees depending upon what we use. Okay, that's why getting it. 007 for so many decades, even today, to this day, Jimmy, I know you know this out in your area. It's the #1 selling wet rotor circulator in North America, and it's not by a little. Okay, it's the best selling by a lot.
It's basically the standard.
Say again?
It's basically the standard. Because somebody said, how come a 007 comes on everybody's boiler? That's the industry standard right now.
Yeah, and it fits. It fits so many different applications. 007 for a fixed speed circulator is the perfect zone valve pump, as we're going to see. It's the perfect zone valve pump, and because it's not too huge, it's a very good zone pump. It's a very, very good zone pump. The only thing that might be a better application for a zone pump might be a 3-speed circulator at low speed. You'd be amazed how often you can use a 3-speed circulator at low speed as a zone pump. You'd be absolutely amazed. But most people set them to high, and we exacerbate the problems we just discussed. Let's take a look at what happens here in a zone valve system, all right, with the circulator. So we have our circulator, okay? And as zones close, as you can see here, as zones close, I get a system curve shift. I get a system curve shift, and the system curves will back up the pump curve. Will back up the pump curve. So as zones close, flow goes down. Okay, even though it's a fixed speed pump, as zones close, flow goes down. Why? Because I have fewer holes for the water to go through. It has to. It has to go down, okay? In most cases, sometimes you have weird system curves that do crazy things, but most of the time, as zones close, flow goes down. And as the flow goes down, because we have a flat curve pump, the head pressure differential does go up, but it doesn't go up by a whole lot. The reason a flat curve pump goes with zone valves like spaghetti goes with meatballs, all right, is because it's a flat curve pump. And as zones close, flow goes way down, but the head pressure differential doesn't go up much at all. Okay. So as zones close, I have a very minimal change in my delta P. Okay. Big changes in flow, very small differences in delta P, pressure differential. Okay. Why is that important? We got to compare it to a steep curve pump. This is a steeper curve pump. This is your typical 3-speed circulator set to contractor, no callback mode. Could be the Taco 0015, the Grundfos 1558, the whatever, doesn't matter. They're all basically the same basic pump curve at high speed. Okay, so yeah, I need 7 gallons a minute at 5 foot ahead. That's my requirement. I'm really, with all zones calling, I'm really giving it 9.5 gallons a minute. It looks what looks to be about 8 feet ahead. Okay, not ideal, but it's not horrible. But again, as zones close, the flow goes down, but look what happens to the head pressure differential. There's a much bigger increase in the head pressure differential. And when you get to closing zone valves against that kind of head pressure differential, you're going to get big differences in delta P, all right? Big differences in delta P, but what else are you going to get? You're going to get banging noises, right? It's going to sound like this. You're going to have banging noises. You're going to get banging zone valves, and zone valves are not supposed to bang. It's not that there's anything wrong with the zone valve, and it's not that there's anything wrong with the pump. The two don't belong in the same sandbox together. The zone valves don't like closing against that kind of head pressure differential, and they're going to let you know about it. Doesn't matter if they're, well, that's because they're installed backwards. No, they're installed forwards. They're fine. Well, you should put them on the return. No, they're going to bang there anyway. There's still head pressure differential. It's still going to bang. Slow acting, fast acting, they're going to bang. Okay, they're going to bang. What we have is a bad marriage between pump and zone valves. We're using the wrong pump, basically. We're using the wrong pump. So how do we fix it? Obviously, stay flat. Flat curve pump on a flat curve pump on a zone valve job, like we said, goes together like spaghetti and meatballs. A steep curve pump in a zone valve job goes together like spaghetti and ice cream. Okay, both good things, but not together, man. Okay, they don't belong together. So in this case, if you need a flat curve pump, golly, why not use a flat curve pump? I mean, it just seems to make sense, right? Why create a problem when you don't have to? I never understood this. Guys say, well, no, I want to use this circulator because it has the 3 speeds and I like that thing, but I'm going to create a problem. I know that. So in order to solve the problem I've just created, you will see guys take a detour and they'll install a pressure differential bypass valve. And they'll think it's the absolute right thing to do. But all a pressure differential bypass valve does in this application is it turns a steep curve pump into a flat curve pump. I'm not the smartest guy on the planet by any stretch of the imagination. That falls to Rick Mayo, okay? But even a guy like me can see why would I create a problem and then solve it when I can avoid creating the problem in the first place by using the right pump? I mean, that's like a Band-Aid for a self-inflicted wound. I don't understand the insistence. And I've seen people say, oh, no, the right way to do it is you have to put a pressure differential bypass valve on that job. Well, why? Well, because if you don't, the zone valves are going to bang. Well, why are they banging? Well, they're banging because the circulator has high head pressure differential. Well, why are you using that circulator in the first place? Because that's the pump I use. Okay, Band-Aid for self-inflicted wound. Next question. Okay. It's just the way it is. This doesn't make any sense to me, but people will do it. I've seen hundreds of these things installed out there in the real world. And I got to tell you, 9 out of 10 cases, it's not necessary if the right pump was installed in the first place. Okay. If the right pump was installed in the first place, you skip step 2. But I insist on using this pump. This is the price I have to pay for insisting on using the wrong pump. It's just the way it is. There are instances where you do have to have them. Absolutely understood. From what I've seen, 9 times out of 10, unnecessary. The other option would be to adjust and adapt. Put in a circulator. It's going to be kind of a chameleon, and that is the variable speed option. Okay. In coming essentials, Rick's going to go through the ECM essentials. All I'm going to do real quickly is just give you an idea of how our circulators work in those applications. Okay.
Hey, John.
Rick's going to get into the real nitty gritty on this. Yes, sir.
One of the things had to do with what you're already talking about, so I want to plug this in there real quick. One of the questions had to do with, hey, wouldn't it be better to use a delta T circulator? T is in temperature. Wouldn't that help, not operate the pressure differential valve as much? But in reality, when we start doing circulators that automatically change their speed, you normally want to take the pressure differential bypass valve out of the equation one way or another. Either shut the valve off to it, shut them all the way so that they don't open up, etc. I just want to put that. We're not going to get in, have the time to get into that exact answer, but just make sure if you're using those variable speed circulators, whether delta T or delta P, normally that means get that pressure differential bypass valve out of the equation. So,
right. You just don't need it at that point. Yep. You just don't need it. Provided you program the delta P or delta T circulator properly.
Yep. Come in next week. We're going to get into that.
There you go. There's a little bit of programming involved. It's not throw it in and it'll figure everything out for you. That's a fairy tale of monumental proportions. So there's a lot of really good questions here, guys. I want to get to them. I want to finish this up and then we'll get to your questions because this is great. You guys are asking really good questions. All righty. Even though these circulators change their speed, okay, even though they change their speed, that doesn't mean system curves and pump curves don't matter. It's still system curves. It's still pump curves. Okay. Well, it's variable speed pump. It doesn't matter. Oh, no, it does. It absolutely does. There's no such thing as a circulator that constantly automatically adapts to whatever changing changing conditions in your system. That doesn't really exist. The VT2218, our delta T circulator, comes about as close as you can get to that, but there's no magic buttons to push on any circulator that'll automatically adapt to everything. That's not how that works. That's not how that works. So we still have to understand system curves and pump curves. Real quick, I want to show you the delta T version, our variable speed delta T VT2218. So let's say that I had that zone valve system again, 7 gallons a minute at 5 foot ahead. Okay, that's where I want to be. I'm going to have a sensor on the hot water pipe going out to the system, and then another sensor on the return pipe, the common return from all of the zones. Another sensor on the common return. All right. And this thing will come out of the box programmed for 20-degree delta T. You can change it based on the needs of a system if you need it to be higher or lower for a specific application, but 20 is pretty standard. The circulator doesn't care what water temperature is going out to the system. It couldn't care less. The boiler's going to set that. It doesn't fight with outdoor reset. All it cares about is the difference between what's going out and what's coming back. So if, say, we're under design conditions, that quote unquote coldest day of the year, and my heat load and everything is dead on accurate, I need 70,000 BTUs, I need 7 gallons a minute, and I'm getting 5 foot of head loss through the piping system. This is exactly where I need to be. Okay, this is exactly what I'm going to get. That's going to be my pump curve. The circulator is going to slow down until I feel that 20-degree delta T on the coldest day of the year with all zones calling. All right. And it's going to work at that speed, which is about half speed, maybe 50% speed. So that's probably going to be about 30 watts. Okay, maybe a tad less. As zones close, I'm taking less energy out of the water. The return water temperature is going to start to go up. That's going to be a signal for the pump to slow down. So it's going to get slower and slower and slower until I'm at wherever my one single smallest zone might be. Okay, maybe it's 2 gallons a minute, and it's going to be at 4 feet ahead. All right. Now, as it gets warmer out, here's the other thing about delta T pumps. As zones open and close on the coldest day of the year, yeah, I'm bopping back and forth between my maximum speed and just my one single zone calling, and I'm going to be going back and forth all day long. But as it gets warmer out, okay, as it gets warmer out, my load goes down. Maybe it goes down to 40,000 BTUs. 40,000 divided by 20 times 500 is 4 gallons a minute. So now with all zones calling, maybe I need to be at 4 GPM right around here. So now this is my new maximum speed with all zones calling. You'll see at that point, I don't have a whole lot of variable speed in this. I'm going to very soon, I'm going to be spending virtually all of my time as a 9-watt fixed speed pump. I tell you what, you're heating your house with 9 watts of pumping power, you're doing really good. Am I going to have a 20-degree delta T through the system at that point? No, probably not. But the point is, I'm not going to have a 4-degree delta T. That's the beauty of delta T pumping. All right. Constant pressure delta P is a little bit different. It varies its speed based on changing resistance against the impeller. As zone valves open and close, I get changing resistance against the impeller. So as zone valves close, I'll get more resistance against the impeller. That's a signal for the circulator to slow down. Zones open, less resistance against the impeller. That's a signal for the circulator to speed up. So let's say here I am, 7 gallons a minute, 5 foot ahead. All right, but I'm selecting a constant pressure 10 foot ahead setting. Maybe it's the Taco 007E. No settings, it's a variable speed circulator, or maybe it's the 0015E3 set to medium speed, 10 foot ahead constant pressure. As you can see, there's a cajillion independent different pump performance curves programmed into the system, programmed into the control brain, okay? So if I were to extrapolate out my system curve, okay, I'm going to work right here. And again, at about 9 gallons a minute at 10 foot ahead. So I'm over pumping still. I'm over pumping still, because remember, there's nothing that magically makes that go away. But I'm not operating at my full 44 watt speed. Maybe I'm down here at about 37 watts. I've just taken a wild guess there. Okay, 37 watts. Now, so I'm operating on this performance curve. A zone valve closes, I get a new performance curve, right? And what it's gonna do, and it takes about a nanosecond for this to happen, I actually intersect up here somewhere on that same curve. The amp draw goes a little higgledy-piggledy, all right? And the control says, whoa, that's not right. We gotta slow down. So what it'll do is it'll drop down. So it's still at this 10 foot ahead constant pressure line, but it'll drop to a new pump performance curve. It's gonna look like that. It's just gonna slide over, okay, and slide over and slide over. But really what it's doing, okay, I'm working on this curve, a zone closes, I go up here and then drop straight down, and it happens very quickly. And as you can see, with one zone calling, I'm here at maybe 20 watts. All zones calling, I'm here at maybe 37 watts. And that's how it varies the speed, okay? That's how it varies the speed. And again, here's a look at the 0015E3, 7 gallons a minute at 5 foot ahead, okay? If I pick low speed, you know, I'm just gonna be working on that performance curve, you know, the whole time. So it's pretty good. It doesn't change with the weather, it just changes with opening and closing, all right? The Delta T pump changes with opening and closing, but it also changes with the weather. All right, cool. How was that? That was fun, man. That was fun. I went a little long, but that's because I talk a lot, all right? So that was cool. We got a lot of questions here. We're going to get to them. I just want to let you know next week, we actually are going to be talking about 3-speed circulator essentials. There's still a place, man. There's still a place for 3-speed circulators, but you got to understand what they do. You got to understand what they do and why they do it, and how it's so tempting to overpump, man. It's so tempting to go, I don't know, contractor, no callback mode. Let's get the hell out of here, you know? that's kind of where we're at with that. So that's going to be next week on
That's right.
Take-O After Dark.
I
How are
was
we doing
jumping ahead.
guys?
We're doing good. We've got lots of stuff. Jim, you want to jump into any of that? I know you've been typing away, and I've answered a few, but any of them jump out at you?
Not really. I mean, the ones that were coming in, John's been answering as he's been going along.
Yeah.
Yeah. Everybody's getting on the right, getting in the right lane here, understanding it.
Yeah. Okay.
There was
one was saying something along. Oh, I'm sorry. Go ahead.
I apologize. There was one where a gentleman wanted to know what would be your decision when it comes to deciding if it's a zone valve system or a zone pump system. And I said, look, if it's a large BTU system, that's a zone pump system. I picked like 130K and above. And if it's below that, to me, it's a zone valve system.
Yeah, a lot of times, the load's going to matter, because if it's a small house and you got three or four zones, right? And each zone, how many BTUs is the load? If it's 40,000, here's an example. All right, we oversize crap like crazy, right? I lived in Minnesota for 22 years, right? You remember, Jim? You drew the short straw and had to come out in the winter a few times, right?
A couple of times, it hurt.
Yeah. Our outdoor design temperature in Minnesota is 15 below, and we routinely blew past that. I did a heat loss on my house, 2,400 square feet, built in 1978, nothing special, 2x6 construction. The windows were replaced in the early 90s before I bought the place, but it wasn't super duper tight or anything. The load on that house, when I actually did the math, was 44,000 BTUs. All right, 44,000 BTUs was the load. Okay, that's 4.4 gallons a minute. If I tried to zone pump 3 zones, split up 4.4 GPM 3 ways, you can't find a pump small enough. You can't find pumps small enough that won't be drastically? That's drastically and dramatically together, right? Dramatically oversized. That's a zone valve job right there. That's a zone valve job. That's a 2,400 square foot house in Minnesota, okay? So where are you at? And what are the loads there? So yeah, you get small multi-zone structures, zone valves tend to make a lot of sense. You get into bigger structures, where a zone might legit have a 4 gallon a minute or 3 gallon a minute load. All right. Yeah. Okay. You can make a case to go either way. Here's the thing. A zone valve pump, say I had 75,000 BTUs. Okay. House had 75,000 BTUs. That's 7.5 gallons a minute. That doesn't mean you're going to have to get a big Mongo pump for your zone valve job. 7.5 gallons a minute. What's the worst case head loss zone you have? If it's 5 foot ahead, I need a circulator to do 7.5 gallons a minute at 5 foot ahead. Okay, that's the Take-O 0015E3 set to low. Okay, just because you got a big load in zone valves doesn't mean you need a big pump. You can still get away. You can still use a small pump, because what was the first thing Jim said to do? Do the math.
Do math.
John,
You're never going to know until you do the math.
Somebody's questioning. They're saying you probably didn't do your infiltration calculation correctly to get that low a number. he's just giving you some, what.
Oh,
He says you screwed up your calc. Is what
I don't
saying.
think so. I don't think so. You know what my fuel bills were? I had a fuel bill that
$50.
No lie, for the winter to heat that house, and we kept it at 70 degrees. Okay. The winter, my lowest fuel bill for the winter, it was 2011, the winter with it never was under $300 for the winter. Natural gas. I had a good system. I'll give you that.
Yeah.
I had a good system, but I did my infiltration right, bucko.
What was your average coldest day that you used? Your design?
Say again?
What was your average coldest day did you use as designed?
15 below.
15 below, $300 for the year. Fantastic.
Yeah. And again, the house wasn't super insulated. It was what it was. That just goes to show if you, I remember we used to teach a heat loss class at the factory where I gave these guys a set of blueprints, like a 2,300 square foot house. It was in Connecticut and it had an outdoor design temperature of 7 degrees above zero, which was the ASHRAE recommended design temperature for that part of the world. It was about 2,300 square foot. And these guys would come and I said, okay, before you do anything, guys, before you do anything, I want you to guess, take your best educated guesstimation at what you think the heat loss is based on your years of experience in the business. And guys would be thinking and they'd be doing these little, 35 BTUs a square foot times 20, they do their little math cheat sheets, and whatever that is. And we had guesses ranging from about 50,000 BTUs up to 135,000 BTUs for this house. The next step was I gave them all the IBR books and said, guys, go to town. Here's how you do the math. Let's do the math. We'll do one room together. You finish the rest on your own. You know what the heat loss of that house was? 30,000 BTUs. Guys go. One guy we figured how much baseboard you needed for a particular room, and this one room needed 3 feet. And he goes, I can't do that. I says, why not? It won't work. You just did the math, okay? It needed 1,500 BTUs. That's 3 feet of baseboard. I cannot put 3 feet of baseboard in that room. Why not? Because it won't work. You just proved it would. I know, but I can't. Okay, that's different than won't. It's different. Can't and won't are two different things. All right. So do you trust the math? Do you believe in the math? That urge to oversize, man, is so crazy because we don't want the phone call, right? Nobody wants it. And why is that phone call always Christmas Eve? Is that a better time than say January 4th? I don't want. I'm okay with the January 4th middle of the night phone call. It's that Christmas Eve phone call I don't want. Yeah, I think in the agita sense, they're both pretty annoying, right? But anyway, the question about the 007E being a variable speed circulator. Yes, it is a variable speed circulator on that 10 foot ahead constant pressure line. As a zone valve pump, it'll be a variable speed pump. As a zone pump, it's not going to be a variable speed pump, but it's where the system curve intersects that 10 foot ahead constant pressure line. That's the speed it's going to run. It's not going to run full tilt, full time. It's going to find, all right, I only need to run at say 22 watts for this one zone, but it's going to stay at that point all the time. Okay. The zone valves opening and closing, that'll cause the pump to vary its speed. Now a delta T pump, when used as a zone pump, will vary its speed depending upon the size of the zone. The size of the zone is going to determine how much it'll vary its speed. You may find if you use a bunch of delta T pumps on a small job, none of them ever get over 9 watts and none of them ever vary their speed. So it is a good idea. I don't know. Am I talking too much? Am I just going on, guys? You guys are both staring at me like, oh, forget it. Yeah. Was it over when the Germans bombed Pearl Harbor? Forget it.
No,
you got the show.
And you're on a roll. It's great. Keep going.
Just call me Butter, baby. I'm on a roll.
Yeah, that's good.
Yeah, most installers install 007s because it comes with the boiler. Yeah, and there's a reason. There's a reason. It's not the right pump for every application, but it's a good pump for most applications. Let's put it that way. And that's just the way it is. Okay. Stanley asked, which one replaced the Bumblebee? That would be the VT2218. In my brain, I call it Bumblebee 2.0, but that's the 2218.
Eric's got one here talking about 007s and having issues. Eric, look at what the requirements were. I can see that in that scenario that you laid out for us with heat exchangers, feeding heat exchangers, flat plate style heat exchangers. Those are really high head, typically high head applications. Again, a 007 is a flat curve, relatively low head circulator. So again, if you're always running that thing way up to the left, not a lot of GPM and a lot of resistance, you're not running in the sweet spot of that circulator. And that might be why you're experiencing what you're talking about there. So again, do the math, figure out what pump should be used, what is the GPM, and at that GPM, what is the resistance, then let's select the right circulator for that.
Here's a highly technical question from our good friend Dan Cook. How are you, Dan? Can you define piggly wiggly? No, but I can define higgledy piggledy, which is what I said. I believe I said higgledy piggledy. Higgledy piggledy is a very highbrow term I learned in philosophy class in college. It means all messed up, all messed up.
You know what? That was a Me Too grocery store is what that was.
Piggly Wiggly, that's right. That's right. I remember going to Piggly Wiggly, and
Oh,
there was
no,
one in Pittsburgh.
Your version was the Me Too, since
The Me
Piggly
Too.
Wiggly was already out there.
Piggly Wiggly, right. But there was a Piggly Wiggly. They opened up a Piggly Wiggly
know.
when I was a kid in Fitchburg,
Yeah.
Massachusetts.
Well, they were kind of a southern thing, I think, for a while.
Yeah,
Yeah.
they're still out there, I think, aren't they? I don't know.
Sure.
All right, what else we got?
We got tons of stuff. We got so much stuff. In fact, some of them I'm just saying, send me a request to this email address and I'll answer you, because
Well, here we go. Here's one. Wouldn't the variable speed always be better, or would the cost eventually outweigh the benefit? That's a really good question, Brian. And I'll tell you what, I think as long as you program the variable speed pump to the best of your ability, to the best of its capabilities, I would say a variable speed pump will always be better than a fixed speed pump. It's going to use less electricity. In terms of cost, I mean, it's nothing. You know, is there $50 difference, $100 difference in the course of a boiler replacement job? That gets lost, right? The way I like to explain it to people is the electrical savings aren't going to change anybody's life, but the electrical savings do in fact mean that the customer is going to buy that pump anyway. They're just not buying it today. Okay, they're going to pay for that pump for as long as they own the system. If you don't give them the variable speed ECM pump, they're still going to buy it. They're going to pay for it for over the life of the system. They're just not going to have it. And I don't know about you. If I'm going to pay for something, I'd like to have it. That's just me. I'm an unusual guy. I'll admit that. But if I'm going to pay for something, I want it. So you can pay for the pump and not get it, or you can pay for the pump and get it. Which way do you want to go?
John,
And then we
Oh,
factor in. I'm still rolling, Jimmy. Sorry, man. And then you factor in, if we set this thing up properly, do we help the boiler operate more efficiently, live longer, etc. Then it becomes a no-brainer. But sorry. Go ahead, Jim.
Well, I was going to add, you taught me this years ago, by asking the question, guys, what do we do? Well, what's our job? And our job is to provide comfort. And I don't know if anybody here has these variable speed circulators in their home, like a Delta T circulator. I do. I tell this story all the time. I have a thermostat at home that's very sensitive. I'm pointing to my wedding ring. And once I put that circulator on, she told me that the comfort level in the house changed, and it's even everywhere we go throughout the house. So, I mean, I'm living it. So I know these things, small as they may be, maybe technically, as we're splitting hairs here, but they do deliver a tremendous amount of comfort. So those are things to think about.
Very good. Very good. All right.
There's one from Jim. With a condensing boiler, variable speed really makes sense. And I think that's a question. There's not a question mark there, but I don't see why there would be a difference. So the condensing boilers are modulating, right? They're modulating based on a set point temperature and a central heating call. You get a central heating call, it looks at the outdoor temperature, it says, okay, thou shalt be at this temperature. That's all it knows. Okay, it doesn't know how much flow is going through the boiler. There's no flow measuring devices in the boiler. It doesn't know if you have a variable speed pump on there or a fixed speed pump on there. Do you see where I'm going with that? So again, you can use variable speed through the boiler's heat exchanger with no issues. In fact, a lot of boiler manufacturers are coming out with the capability, and some of them are even packaged with a 0 to 10 that varies the speed of the pump based on the delta T that you want to run the boiler at. Doesn't have anything to do with firing rate or anything. It's just you set it up to run that boiler at a delta T of say 30, 35, etc. And that circulator will vary its speed to maintain that delta across that boiler's heat exchanger. That's absolutely acceptable. In fact, that's a really good way to run these systems. That way you get the lowest temperature back to that boiler. And that's what we want with modulating condensing equipment. So
Very cool. Here's a good question from Zach DeVoy. Why in this example do we not run the pump in proportional pressure mode? Interesting. Proportional pressure is, in my view, useless in an on-off zone valve job. Because what does a proportional pressure curve do? It kind of goes down. As flow goes down, the head pressure differential created by the circulator goes down. That particular performance curve was designed specifically for your continuously circulating systems with thermostatic radiator valves that are opening and closing based on how warm it is in each room. The theory is, as it gets warmer out, those thermostatic radiator valves are going to be more closer than they would have been when it was colder out. So the required flow for the radiators go down, and as that required flow goes down, the head pressure through those runs to each radiator will also go down. In a zone valve system where you're either open or closed, open or closed, open or closed, when it gets really cold out, what could conceivably happen and what we've seen happen is if you pick a proportional curve that actually meets your highest flow and total head number, it may not be able to meet certain combinations of zones that have lower flow but still are at a high head. And you get into that situation where that ain't working. All right. It works when all the zones are calling, but when some of the zones are calling, it doesn't. So that's why we wouldn't use proportional pressure mode. It's one of those things that it's very European and it's very cool because it's European, but it's very impractical for the way we do things here. Now, you may find in some light commercial applications, Rick, you taught me this, where you have like a 2-pipe system with zone valves, where maybe a proportional pressure setup would actually work and work very well.
It works well.
Residential applications, not so much. Go ahead.
So with that said, March 3rd is when I'm on the hook for the ECM Essentials, and we're going to spend most of the time looking at pictures of piping diagrams and having you, I'll do an explanation of why you would use this particular mode for that application, and I'll go into that in depth. So anyway, those who aren't, well, again, we pull a box out, we pull a circulator out of the box on the job. It's midnight. You don't have time to do the math we keep talking about, but wouldn't it be good just with a couple of little tips to know what mode to run? And that's what we're going to cover on March 3rd. Yeah, March 3rd. And hopefully that'll answer a lot of your questions. There are absolutely applications where zone valves would be used in proportional, but it has to do with a piping scheme, and we'll clarify all that and we'll try to make it as easy as possible.
Excellent. Here's another good question from Jim Tamblin. Why wouldn't you set delta P where you get system design flow? Well, that's going to depend. That's a really good question. That's going to depend on the type of circulator you have. Most circulators have specific settings, like our 0015E3 has 5 foot ahead or 10 foot ahead constant pressure delta P. You pick one or the other, which one makes the most sense, right? You get into our 0018E with a Bluetooth connection to an app. In the app, you have 9 different constant pressure curves. So you've got so much more flexibility within that same basic pump curve with the 0018E. So yeah, it depends upon the capabilities of the circulator. How many constant pressure settings do you have that will allow you to get to where you need to be? There's not a pump out there that has more constant pressure settings than the 0018E. That's an amazing circulator, absolutely amazing circulator. All right, we got a lot of good questions here.
Oh man, it's unending. You know, it's unending. Jim, are you? I'm trying to type some of this in, but anyway. We'll try to get to as many as we can. But
there's some here that are kind of related to doing the math. Really, like, you know, what I'm getting is if I'm replacing the boiler, you know, I should be doing the math because I can take advantage of extra oversized baseboard, because one gentleman said that most systems in this area are always oversized. Yeah, that's an advantage you'll have if you do the math, and you'll have more options when you're giving a price to a customer, because, hey, you could do condensing, and if that's too much, you could do cast iron still with outdoor reset and a delta T pump. or you could bring it down to just a standard plain Jane cast iron with nothing special, and you'll still have a better price than your competitors because you got everything sized right. A couple of those have been floating around there, so.
Yeah, I've actually talked to guys that say, hey, if I go in with a smaller boiler than my competitors, the customer's gonna think I'm doing something wrong and they won't hire me. Which I think, oh, yeah, okay. So if Johnny Finnegan jumped off a bridge, does that mean you'd have to as well? I mean, really, we learned that one when we were real small, right? You know? And my mother always used Johnny Finnegan too, because Johnny Finnegan was the kid in our class who was just the dumbest, dumb as a box of rocks. And you know, if he did it, would you do it too? I said, yeah, you know what? I really wouldn't, because he's dumb as a box of rocks. But that's besides the point. Probably sharing a little too much, but you know what I mean. But yeah, there's doing things right and there's doing things wrong. I mean, I guess if you're going to go to the trouble to do the math and you're confident in your numbers, you share that with your customers. Saying, look, did these guys do a heat loss calculation? Well, no, they just sized it off the old boiler, and the old boilers always work. Well, yeah, there's a reason. You know, it's always worked. It's dead now, but it's always quote unquote worked. You know, if you do finished carpentry with a sledgehammer, the wood's going to stay together. You know, it's not going to be pretty, but it's going to stay together, and you're going to work harder than you need to. How about we do some math. This is a science. It's not a, this isn't preschool. You know, we do some arithmetic here. We find out what your house needs and we size appropriately. And the benefit to you, Mr. Customer, is you're going to have a system that's sized right. It's going to be more effective. It's going to be more efficient. It's going to last longer, and we'll have a lot fewer problems. And then if this guy was your service customer, you go back to say, remember, for the last 10 years, I've been back fixing this, 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 and this. Do you ever wonder why that stuff was happening? You know, there's always it opens up a discussion. When you do something differently than your competitors, more often than not, your customer wants to know why. What's wrong with you, right? You know, and then that gives you the opportunity to talk.
Yeah.
And be the professional.
Set the level. Don't let your competitors set the level. You set the standard. Yeah.
That's it. That's it. When you let the other guy define the parameters of the battle, it's not pretty.
David's got a question about delta T. He says, does the 40-degree delta T system allow the condensing boiler to operate at a lower return temperature and higher efficiency? Well, on a condensing boiler, yes. Well, again, I just say this, David, just make sure the boiler manufacturer, in the back of their book, they'll always tell you what they will let you go out to, meaning how wide of delta T is acceptable. As long as it's in their book and as long as it's in writing, okay, go for that biggest. In fact, we've got some sessions where we talked about circulator sizing on ModCon boilers piped in a primary secondary configuration. And the key to the takeaway from that is, yes, go with the biggest delta T that the manufacturer in writing lets you do. And you'll see a much better performance in that whole idea. One of the questions earlier was, what does it mean? Somebody didn't understand you, John, when you were saying short cycling. They didn't have, they couldn't understand why that was a negative thing. So somebody else expound on that. I know, but I just was talking. So go ahead.
All right. Jim, you gonna take a shot at it? Why is short cycling bad? You're a boiler guy.
Yeah, and I lived it. So here's, if it's your own house, oh yeah. If it's your own house, every time that boiler's going on and shutting off really quick, imagine it's just reaching into your pocket, taking out money. You can't get any plainer. It's just taking money out of your pocket. On, off, right?
Yep. Talk about the lowered life expectancy of the equipment.
Yeah, it'll just
here. I'm gonna turn my lamp on, off, on, off, on,
nice.
off. If I kept this up for the next, I keep this up for a while, I'm gonna wear that switch out, right?
And the bulb, maybe.
And the bulb, yeah.
And the fan, and the igniter, and the relay. You see where we're going with that? It's on and on and on.
Yep, that's it. That's it. So yeah, none of this is good. Our good friend Anthony Reichow. I know, Jimmy, you know Anthony very well, and
very well.
He's a good friend to us all. One of our favorite humans on the planet. Of all the two-legged people I know, he's definitely one of them, and I love him like a brother. But Anthony, Anthony was a service for his rep company, and they sold a line of boilers where the control, modulating condensing boilers, where the control would keep track of cycles and runtime. Total runtime, total number of cycles. They had to go back for something weird. I don't know exactly what it was, and what it was really is important to the story. They figured they'd check the control just to see how it was working. And they saw the number of cycles and the number of run hours. And this boiler had been maybe 18 months or something like that. And it looked screwy. It didn't look right. And they said, geez, that looks like that's out of whack. So they did some math, divided the number of run hours by the number of cycles. And what they found was that boiler's average runtime was about 14 to 15 seconds.
Oh, gosh.
I don't know if a boiler has enough time to get efficient if it's running for, on average, 14 to 15 seconds. And somebody pointed, well, obviously it's going to run longer in certain time. Yeah, okay, maybe it's going to run for a minute or two at best, you know, and then other time, if for that to be true, other times it's got to go on for like a half a second to make that a 14-second average. Boiler was oversized, the system was overpumped. Myriad of problems led to this, okay? But it came down to size the boiler right, size the pumps right. Okay, doing one without the other is half a measure. You know, you don't want to do half of your parts and not a system. You're going to do a system. You size the boiler right, you size the pipe right, you size the pump right, you size the heat emitters right. What did Lombardi used to say? You don't do things right once in a while, you do them right all the time. My father used to say that too. It didn't click, but eventually it did. Do things right all the time. That's just the way it is, right? How we doing? More questions?
You know, basically, we're always talking about the fundamentals over and over and over again.
Mm-hmm.
Right?
The fundamentals never change. That's the
No,
thing.
and if we nail them all the time, most of our problems disappear.
Yeah, you'd be amazed. You'd absolutely be amazed. Yeah. Here's a good one from Kenya Clay. You mentioned a buffer tank. When would that be recommended for the system to add volume? Do you have any guidelines or suggestions? Oh gosh, yes, we do. We do. Buffer tanks. A buffer tank is, you all heard of low loss or hydraulic separators, right? That all the cool kids use. You know, you see them. I like to look at on Facebook, you know, and on the hydronic heating techs and all these other Facebook groups, and the cool guys all have hydraulic separators. Yeah, if you don't use a hydraulic separator, you just aren't cool. All right, you'll get beat up at school tomorrow. It's the way it is. A buffer tank is nothing more than a big hydraulic separator. Has water volume. Why do you want a big one? Well, again, it goes to that short cycling thing. We want fewer longer cycles as opposed to more shorter cycles. Adding water volume helps because a lot of ModCon boilers have what, Rick? You know, 1.5 quarts of water in them.
Well, depending on the heat exchanger, right?
Yeah.
A lot of people are using fire tubes now, and they have a lot more water in them than the water tube style. So.
Right. So it depends. Again, depends on the boiler.
Yeah.
What a buffer tank does is, if you have a lot of small zones, microzones, we see this a lot with Radiant. Okay, you have microzones where the smallest zone is smaller than the lowest firing rate of that boiler. All right, you're going to want to add a little bit of water content to that. And there's a formula for figuring it out. We can go through that in subsequent classes, but it'll help you decide, do I need a 5-gallon tank, a 10-gallon tank, a 20-gallon tank? It's going to depend. In some cases, you may only be able to find a 10-gallon tank, and that's what you use. You know, it's because it's better than not having it. But what it does is it allows you to maximize your runtime. We use a target of a 10-minute runtime, meaning every time that boiler fires, we want it to run for 10 minutes. Okay. Way to think about it is, it's a big tank of water, heated water. Your zoning doesn't necessarily fire the boiler. Your zoning opens and closes zones, and you're circulating water from the tank out to the system. What tells the boiler to fire is the temperature in the tank. If the temperature in the tank starts to drop below where you want it to be, it'll tell the boiler to fire, and you bring up that whole tank up to temperature, and we have nice long run time. So that's kind of where we're going. If you have like one zone, like it's an old, you know, monoflow T system or big single zone system, reverse return type of thing, you probably don't need a buffer tank. All right. You probably don't need a buffer tank. If yes, your basic moose antler piping system is going to be just fine. If you have multiple zones, but they're not smaller than the smallest firing rate, then either the moose antler, primary secondary piping, or a hydraulic separator to make it a little easier as a convenience side. It makes a lot of sense. If your zones are smaller than your lowest firing rate, a buffer tank is just, it prevents the whole system from becoming a quote unquote time bomb, meaning something's going to die on you at some point.
Another point, John. Some of the boiler manufacturers will actually put in their in their manual what the minimum flow rate through their heat exchanger should be. And if any of your zones are smaller than that, then you're going to have to compensate one way or another. That's with a low loss header, 2 pumps, buffer tank, 2 pumps, that sort of thing. So again, the boiler manufacturer will tell you what they're concerned with, and it normally is associated with flow at certain firing rates. And so we've actually covered some of that in some of our other classes. So again, just defer to them, and that'll help make a decision. As John said, it's usually not smart to put in a hydraulic separator for the sake of being cool. Yeah, you really only should be using them when you need them. So
right, there you go. There you go. Here's one. It's okay to put in too much baseboard. We can run lower water temps at design conditions and condense for more of the season. That's an interesting point. I'm glad you brought that up, Bill. A lot of guys will say, I've heard said, well, this is a baseboard system. It's stupid to put in a condensing boiler. You got to run it at 180. It's just a regular boiler. It's a waste of freaking money, blah, 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 blah. Well, yeah, I suppose, but we've all seen the old fashioned way of sizing baseboard, right? I know you've seen it, Jim. What's the old fashioned way of sizing baseboard?
Every single wall, cover it.
Yep. And what if there's a door in the way?
Yeah, stop it there and just pick it up on the other side.
Yeah, or you wait. I tell you what, the guy that invents hinged baseboard is going to be a jillionaire. I'm convinced of that. But you see it, every inch of outside wall covered with fin tube, with element. Why? Because I can, and I'm not going to get the phone call in the middle of the night, Christmas Eve. All right, January 4th, I'm okay. Middle of the night, Christmas Eve, no. So it's overradiated, clearly overradiated. The whole house is overradiated. So when guys go in to replace the boiler, one of two things happen. They either look at the output plate on the boiler they're taking out, yell up to the homeowner, hey lady, does this boiler work fine for the last 40 years? As far as I know. All right, that's the size boiler we're putting in. Okay, very analytical. Or you get smart and you say, well, I'm going to measure the feet of baseboard. All right, multiply that by 500 because the boiler's got to support the installed load here, right? I got 273,000 BTUs worth of baseboard in this 1,900 square foot ranch. I need that size boiler to support that radiation. So that either way you're doubling down on somebody's mistake. So you do the boiler doesn't have to support the installed radiation. The boiler has to offset the heat loss. Remember, the output of fin tube baseboard, the output of any radiator is going to vary depending upon the water temperature you run through it. Nothing says you got to run a $180 through baseboard, right? You get different baseboards will be rated down to 140, 150 degree water temperature. I mean, heck, slant fin rates there's down to 110.
Yep.
Do the heat load for the house. Find out the heat load for the house. Do a room by room heat loss so you know what each room requires. Then you figure out how much baseboard's in each room, and then you backwards engineer it. Now it's not how many BTUs do I need. I know how many BTUs I need. What water temperature do I need based on the radiation I have available? You'd be surprised. Maybe you only need to run 140 degree water or 130 degree water through that baseboard on the coldest day of the year to still heat the house. Now you've really done something. That makes me happy.
Yeah. We have some interesting things happening in my territory because of COVID and people running out of the New York City or any inner cities, and they're coming to the burbs. And they're buying houses as is.
yeah.
Right? So it's a seller's market, it's incredible. So where am I getting at here? I go into a lot of these houses, so my daughter's looking to buy a house. She's getting married. I see baseboard everywhere. I mean, there's not a spot where there's baseboard. So you know everything's oversized. And there's money to be made if guys would go in, do their calculations. They'd have so many options for Mr. and Mrs. Smith on these homes because these boilers have to be replaced too. They're at the end, you know, opportunity. So it's all out there. Just do the math.
And when you give your customers 3 options, good, better, best, 7 out of 10 times, where do they go?
Yeah.
Yeah, they'll go right into the middle. Mostly, they'll go to the middle. The rest of the time, they're going to go for best more than they're going to go for the bottom end. Because when it's for your house, you'll buy better than you need or better than you think you need because it's your house, right? I went to a speaker once. You remember Larry Steinmetz, right, Jim?
Yep. I bought the book. You told me I bought it. I read it.
God rest his soul. What a wonderful, wonderful man, and a nice gentleman. We lost him about 8 years ago now, and I hear his voice every once in a while. Very distinct, just a wonderful gentleman. And but he was a great trainer of sales. He could teach you to sell ethically, but logically, you know. And he said, he asked me once, do you know what the #1 selling tire is on the island of Oahu in Hawaii? And I said, I haven't the slightest freaking idea. What is the #1 selling tire on the island of Oahu? And he told me, and it was the highest grade Michelin tire they make.
Okay, why?
I know. I said, where the hell are they going to go? Places like 20 miles around tops. Where the hell are you going to go? Why do you need the best tire Michelin makes as the #1 selling tire on the island of Oahu? He says, when it's for yourself, you buy the best you can. You know, you want a good tire, right? You're 18 miles from home and you got a blowout. Well, what are you going to do, right? No, they just, when it's for you, you'll buy better than maybe the conventional wisdom is that you would need.
That's right.
It's true. You think about it, it is true. You don't regret buying better.
Nope.
You do regret buying worse. You do regret going cheap.
Yeah.
Most people don't regret going better. They really don't.
Buy cheap, it's going to cost you more because you're going to replace it again sooner. It's going to already pay for the better one regardless. Just do it.
Nobody. Yeah, it's that whole thing about being the habitual low bidder. It's not a prize. It's not something you would want to aspire to. Here's another question. This is from Zach. And Zach, I don't know, maybe if I answered this one already, would you please tell me? Yes, why would you run constant pressure versus proportional pressure coming from a zone valve background in design? I think I answered that, Zach, but let me know. I'm not sure if this question came in before I answered it or after.
He said yes.
You said yes, I did answer it?
Yeah, yep.
Okay, good. Then I'll skip ahead. Very good. Thank you, Zach. Appreciate it. Let's see. What else do we have here? What is the equivalent to the Grundfos 4344? Ask Rodney. And Rodney, you have your audio back. Excellent. I'd say that's the 0012. I think it's the 0012. It's more of a higher flow, lower head, flat curve, 3-speed pump. I believe that would be our Takeo 0012, Rodney, if I am correct. I think I am. Please send me the math to do a system curve. I'm still a little lost. I'm gonna grab something here. Do you guys have your if you have your screen set up to show you webcams? Okay, set that up so you can show webcams, because I'm gonna grab my system sizer wheel and I'll show you that. And the math I'll look up for you real quick too. So you guys talk amongst yourselves. I'll be right back.
Hey, one thing you could do when you want to know what the actual system curve is just to figure out one point where the pump is running. You simply are going to look at the circulator running with all the zones open, and if you can, measure the outlet pressure and the suction side. So suction and outlet differential pressures of the pump. We can take that to the circulator performance curve and find out where it's running on that maximum speed. From that point, we can actually calculate what the system curve is based on the math that John's going to share with you here in just a second.
Whoops, wrong folder. I'll be with you in a second, guys. Keep talking.
Okay. Got another question, Jim? that jumped out at you?
Actually, I'm looking at one from Zach about Juan McLean Evergreen boilers. Do you see that, Rick?
Yeah, we actually have Dan Cook on from Weil, but we should keep this fairly general. So, just Zach, that would be a good question for you to direct to your salespeople that sell you that product. I think it's just a matter of enough availability of the larger circulators that do what they want it to do. As you can see, they've used it for the smaller boiler. They're just a matter of stepping up to ECM and the variable speed capability in the larger units. And you're referring up to about 400,000 BTUs. So.
Okay, I'm going to take the con back here real quick, guys.
Go ahead.
And share my screen. Well, actually, before I do that, if you can enlarge, you viewers out there, you figure out how to enlarge your my webcam, so I'll take up your whole screen.
Put your mouse on, John. Put your mouse. Put for the folks out there. Put your mouse on John's screen. You'll get an arrow in the lower right-hand corner that points down and up. Click on that. It'll blow him up. Yeah, not literally, but.
All right, this is the, there we go. This is the B&G system sizer wheel. Okay, and it does a lot of the calculations that we talked about. GPM equals BTUH divided by delta T times 500. It helps you figure out flow. It'll help you figure out head loss and resistance and different things for your system. On the back, there's something called scale number 5 right there. You see scale number 5. And on scale 5, you have in the white window, you have your flow rate, the required flow rate, and up on the top, you have the head loss. So again, let's say my load here is, let's say I'll do 7 gallons a minute at 5 foot ahead, okay, because we did that. We did that one, 7 gallons a minute at 5 foot ahead. Okay, so let's see if we can see that. Yep. You see I'm at 7 gallons a minute at 5 foot ahead. If I go lower in the white window, I go to 6 gallons a minute. And what this thing does, and it was invented by Gil Carlson from Bell and Gossett years and years ago, it's doing the math formula for you. All right. So 7 gallons a minute at 5 foot ahead. What would the head loss be if I was running 5 gallons a minute through that zone or through that system? So I look at 5 gallons a minute, and it looks like it's about a little more than 2.5 or just exactly 2.5 feet ahead at 5 gallons a minute. Let's go down to 3 gallons a minute, and you'll see I'm at less than 1 foot of head. So those would be 3 points on the plot. Let's go look at the other direction now. So at 7 gallons a minute, again, I'm at 5 foot ahead. At 8 gallons a minute, I'm at 6.5. At 9 gallons a minute, I'm at 8. 10 gallons a minute, I'm at 10. And you continue, 20 gallons a minute, I'm at 40 feet ahead. So that's how you get the different points on the plot. And you just dunk, 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 and then connect the dots, and there's your system curve. Okay, that's the easy way to do it. The math, okay, is I'm going to share my screen real quick. Okay. All right, and I'm going to show you right there. There's the math. Okay. Head 1 divided by head 2 equals flow 1 divided by flow 2 squared. Head 1 and head 2, or I'm sorry, head 1 and flow 1 are what you know. Okay. Head 1 in this case, 7 feet ahead divided by head 2 equals flow 1. I'm sorry, I was 5 feet ahead, and head 1 is 5 foot ahead. Flow 1 is 7 gallons per minute. Then we put whatever we want into flow 2, okay? And then we'll figure out what head 2 is. And then it's just algebra, okay? Then it's just algebra. And let me show you how that works, and then you'll see why I didn't want to bother going through this during the class. So here we have, let's do the math, 3 gallons a minute at 6 feet ahead for this particular example, all right? Head 1 divided by head 2 equals flow 1 divided by flow 2 squared. So let's fill in what we know. 6 feet ahead is head 1. 3 gallons a minute is flow 1. Just for giggles and grins, I'm going to plug in 6 gallons a minute because I want to know what the head loss would be if I was running 6 gallons a minute through here. I put in 6 gallons a minute for flow 2. Okay. So now it's going to be 6 divided by X equals 3 divided by 6 squared. Now 3 divided by 6 is 0.5. Okay. So 6 divided by X equals 0.5 squared. We're getting into algebra again. That's stuff we swore we'd never use. So let's further simplify. 6 divided by X equals 0.5 times 0.5, that's 0.25. To solve for X, first thing I got to do is multiply both sides by X to get rid of the X on the left-hand side. So 6 divided by X times X equals 6, all right? And 0.25 times X is 0.25X. Now to solve for X, I divide both sides by 0.25, and now I find that at 6 gallons per minute, my head is 24 feet ahead. All right. So there's the math. I'm glad you wanted to know that. Okay, that's why I always reach for this thing first. But I'm glad you wanted to know that because that's the math for actually figuring out. Then you want to find out what another point is, just go back to the beginning and put in, 4 gallons a minute as flow 2. Or 1 gallon a minute as flow 2, and do your math that way. You put in whatever you want for flow 2 and you work backwards to figure out what head 2 is, and those will give you your points on the plot. You plot them down, put them on the plot, connect the dots, and there's your system curve. Right. Coolness. I hope that was fun. And again, doing it this way, as you can see, was just a lot quicker. All you got to do is line up. In this case, it was 3 gallons a minute at 6 foot ahead. Let's see, 3 gallons a minute at 6 foot ahead. Where the heck are you? There's 3 gallons, I can't see. There's 3 gallons a minute at 6 foot ahead. So right now I have that at 3 at 6. Okay, go up to 6 and you see we're right about 24. Okay, off to the other side there, 6 is right around 24. So again, this does the math for you, makes life easy. Cool. Will a delta T pump turn off if there is 0 delta T through the system? And what it's going to do, it's not going to turn off, it's just going to hit that minimum speed, and that's all it's going to do. It's once it hits minimum speed, that's the speed it runs. Doesn't matter what the delta T says at that point. It goes slower, slower, slower till you hit minimum speed, and that's it. Okay, it can't go any slower than that. And that was a trial and error thing. We learned that one the hard way, but that's just how it works. Okay, cool. If you're replacing a circulator on a job that all info is gone, where would you start for sizing? Oh, Jim, I'm sure you've done this. Go to a job site and there's nothing, man. What do you do?
There's never anything, or the emails I'll get is, hey, I've got 200-foot loop and radiant, and there's 2 loops. What pump? So it's based on GPM and head. We have to figure out what the BTUs are. I mean, we just have to gather all the information. So we have to do homework.
Mm-hmm.
We got to start taking measurements. We got to start doing some calculations. We can always wag, I mean, I'll give you what did John tell me years ago? I'll sell you the Binford 1000. Never forgot that. Thought it was the best thing I ever heard. So sure.
That's the Binford 5000. That's what I heard anyway.
Yeah. Okay. Well, we've expanded. We're now up to the Binford 10,000, right?
Oh,
that's just contractor no callback mode, right? Again, that's why people would gravitate towards a 3-speed circulator for just that reason instead of a 008, where high speed on a 3-speed circulator, whether it's a Grundfos or a Takeo or whomever, is basically a 008. People would rather have a 3-speed circulator and turn it to be a 008 than install a 008. Because there was an illusion of control there. I'm getting more. Give me it all. She's got, Captain. Same thing. Good question from Bob Dressler. Are they using 008s in Europe? No, we never sold 008s in Europe. They would use the European equivalent to a 008, okay? Whether it was by Grundfos or Velo or any of the other European pump manufacturers, they would definitely use the European equivalent of a 008, the same pump, same basic performance curve. But now what they're seeing, I think, is Rick, when did that mandate in Europe come? Do you know? It wasn't all that long ago. It was maybe within the past 4 years.
You're talking
Where
ECM for efficiency, right?
yeah, where they actually mandated ECM circulators, even though ECM circulators had been around in Europe since 1999, 2000. All right,
probably 8-9 years ago, probably something like that. Yeah,
they finally got around to mandating them for use there. And people say, well, when's that going to happen here? Who knows? You know, we thought 2023, 2024, that may or may not be back on the table. It's going to happen. We just really don't know when. So until then, we are still making and innovating fixed speed circulators, because there are people buy a ton of them. Like I said, the 007 is to this day the #1 selling wet rotor circulator in North America. So we do sell a bucket load of those things.
Patrick's got a question about delta T differentials across, the system side and the boiler side. And Patrick, you probably know that answer. You just want us to talk about it, right? Anyway, what we typically see is a tight delta. Let's say a radiant system where they ran the tubing at a single wall serpentine and they want tight delta of say 10, 15. But you want that boiler's return temperature to be fairly low, and you don't want any short cycling of that. You might stress the delta out on the boiler to say you've got an example of 40, and we might have the system at 20. I guess, can it be done? Absolutely. Should it be done? You should do the math, and again, refer back to that boiler manufacturer that says, you can run my boiler out to X, and use that number in your calculation on the boiler's primary pump. So.
Do the math, because it'll affect the pipe size.
Yep.
Do the math.
Yeah, save you some money, right?
Big time.
Absolutely. You know the difference between a 1-inch air separator and an 1.5-inch air separator? Your system side might need to be 1.5 inches, but doesn't mean you have to use an 1.5-inch air separator. So anyway, little things that can save you some bundle of money if you'll just sharpen your pencil. So.
All right, let's see. A system with a manifold actuators for zoning radiant, one pump in a system. Is that a delta P potential application? Says Robert Benedict. Yeah, sure. It's also a delta T application too. But either one.
Either one.
Yeah, either one. Here's how I determine whether to use a delta T or a delta P pump. And let me backtrack a minute. In virtually every instance, I have found a delta T pump will perform better than a delta P pump. In virtually every instance, the difference is scale. In some cases, the difference is like this. In some cases, the difference is like this. And in some cases, the difference is like this. And then it becomes a value proposition. Is it worth the additional cost at that point? And what determines whether it's this, or this is the size of the job. Okay, it's the size of the job. If you want to use a delta T pump as a zone pump, okay, let's talk about a big zone here. Okay, that should be a good size zone. 40,000 BTUs, 4 gallons a minute, 9 or 10 feet ahead. Now I've got a lot of range for that speed to in fact vary. Okay, 2 gallons a minute at 4 feet ahead, I'm going to vary my speed that much. Am I getting my money's worth? Okay, am I getting my money's worth? I'm going to spend most of that heating season with a fixed speed 9-watt pump, which isn't bad. There's never anything bad about that. But could I get close to that same performance for less money, to the point where, yeah, that variable speed is not helping me much? I think you could. If you were to go with a 0015E3 set to low speed at 5 foot ahead, okay, it's not going to vary its speed. It's going to be a fixed speed pump, but it's going to be performing real close to where the other one was. Okay, for a fraction of the price. So that's okay. The difference is like this. Okay, so it's going to be the size of the application, Matt, rather than the type of application, if that makes sense. You know, so there are other examples, like if you were to use the 0018E, which is that Bluetooth pump where we can set it up a bunch of different ways. Now there's a zone pump. If you needed 2 gallons a minute at 2 feet ahead, by using my app, I can set that sucker up to give you 2 gallons a minute at 2 feet ahead, and you can't get a heck of a lot better than that. Okay. Now it's okay. Where do I go, and what level of complexity am I, as the installer, willing, going to work with, or where's my job? Where am I going with this? Do I offer good, better, best, and do I change which circulator I use in good, better, best? Sure, you could surely do it that way as well. But there, in every instance, I would say Delta T is a superior pumping technology to Delta P. It's just a matter of how different is it, and that's going to be on size. That's one of my favorite questions.
Dan Cook is just pointing something out. He's another one of our boiler manufacturers that has to deal with things all the time, and he says, you know what? I'm kind of adding some things to his statement here, but every one of those boilers nowadays has a reading you can look right at and see what your supply temperature is and what your return temperature is. If it's a ModCon condensing piece of equipment and it's running at a 5-degree delta T, guess what? Change the speed of your pump because it's pumping too much. Again, people say, well, you can't determine that till you're on a designed day. Well, yeah, you got a point there, but most of the time, if you start seeing very tight temperatures across that boiler's heat exchanger, you're over pumping. It's pretty simple. Okay, we can show you the calculations and the math and all that stuff, but the good thing about it, most of those circulators, and especially nowadays, you even got ECM variable speed capability, but you can turn the speed down on those pumps. I would say turn it up on high to start, to purge, to get that wet rotor burped, so to speak, and then turn it down to low and watch and see what happens. Okay, a lot of this, especially with ModCons, are pipe primary secondary, so the only responsibility of the boiler circulator is to pump through a tank of water, through 2 T's or a low loss header or something like that. Its responsibility is very, very low. So that should cause you to think about turning that pump down. Okay, and the evidence is in the boiler itself. So Dan, I hope that did what you wanted it to. So.
Bob Dressler asked, you didn't touch on how to find head for a system. You know, we didn't do that tonight. That's actually going to be part of next week's program. How to calculate head versus how to estimate head. And there are going to be instances where estimating head is all you can do. All right, that's better than nothing. But we will show you the difference between calculating and estimating, and how that applies specifically to 3-speed pumps, but any kind of pump you're looking at.
That was a question earlier about why aren't we just using the 0.06? And I said, we're just guessing. Really, it's an estimate. It'll work for you, but there's a better way to get there to get a better idea what that pressure drop's going to be.
Yep, absolutely. Rodney left, but this is a good question. How do we deal with a pump with an engineer who drastically oversizes both boilers and pumps? You say, what is it? You say, sir, I'd like you to sign this performance waiver that says if anything goes wrong, you're the engineer. I just put in what you told me to.
That's right.
And it's any problems, it goes back on you, cowboy.
Yep.
That's how I would deal with it. Yeah, because what is it? You can always tell an engineer, you just can't tell them much. And if there are any engineers, don't write letters, people. Okay, it was just a joke. Okay?
There's plenty of great engineers out there that we work together with.
And I tell you, if you're an engineer and you stuck out this long on our presentation, you have my absolutely undying respect. Because number one, you went to school a lot longer than I did, and you have my respect. Absolutely.
Indeed.
Absolutely. Yeah. So don't write letters. It was just a joke. but I've had to deal with engineers. I remember an engineer. I had been in business forever. He came into my office when I worked at a rep in Boston, threw a set of blueprints on my desk and said, I want you to design the radiant system for this house. I said, sure, that's what I do. I'm happy to do that for you. And he said, I don't care what you come up with, but whatever heat loss you come up with, you double it, okay? You double it. I said, why would I do that? Because I've been in business 30 years and I've never been sued in 30 years. This is my first radiant job. I'm not about to get sued now. You double it or I don't sign off. I said, radio. We could not have physically gotten more pipe into that house. There was no room for more pipe in that house. We did the floors, the walls, the ceilings. You know, we did wrapped the bathtub. I mean, there was pipe coming out of the wazoo in that house. They weren't cold. Nobody got the call at Christmas Eve. Boy, it was a lot of pipe.
Yeah. Dan's saying, yeah, people always blame the boiler when things aren't working, you know, and it's rarely the boiler's fault. Just like they point the finger at the pump too, you know, it's like, yeah, the pump's not, yeah. But anyway, if it's got a name on it, that's who they're going to blame.
Here's a good question from Eric Contini. Does TACO have a domestic hot water recirc pump that utilizes a timer and a return water temperature control, or is the smart plug the main smart option you use at the moment? Well, good question, Eric. We do have both. We sell domestic hot water recirc pumps that have a timer, okay, either the dippy switch timer or a digital timer that you can program, and you can get an aquastat with it to connect and turn the pump off on temperature. You can absolutely have that. Or the smart plug is simply it's the modern way to control a domestic hot water recirculation pump. It's learns your domestic hot water usage patterns and then repeats them for you. And it constantly changes as your patterns change. Now, one of the things that's happened with people being home all the time, all right, is nobody has normal hot water usage patterns anymore, or at least a lot of people. Well, I can't say that I don't have normal hot water usage patterns anymore. So, you know, you may shower at 7 o'clock one morning. You may not shower till 3 o'clock in the afternoon the next day, or you may wait a couple of days. Where are you gonna go? Who cares? You know, that kind of thing. So there's no normal usage pattern. So what you can do with the smart plug is simply put it into what we call the pulse mode. And that means it'll be 5 minutes on, 10 minutes off, 5 minutes on, 10 minutes off, and do that 24/7. So no matter what time of day or night you turn on the faucet, you'll have hot water. And it's a darn sight better than running a pump 24/7. Way better. And Rick is going to go over this in a few weeks, right? About sizing domestic hot water recirc pumps. Oh my God.
And show you an app that makes it really easy. Yeah.
Think small. Think small. Small is good. And anything with time is really your benefit, to your benefit. Small, 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 small. Otherwise, you are going to have liability issues, or someone's going to have liability issues when that piping system turns into a sprinkler system. Just saying. Rick will wow you with that, man.
Jim, do you see anything you want to jump at? There's several. I mean, this just keeps going. We might be here for a full 3 hours. I don't know. You just never know.
I know.
There's a lot of ways.
You don't have a life, do you, Jim?
Questions, but to jump on what John just said about things small, we've had a bunch of houses on Long Island, you know, these mansion houses where the recirc line was hex, all worn out, over pumping.
Yep.
Yeah.
What's the kryptonite for any
cover
pipe?
that.
Yeah. Kryptonite for any pipe. Hot, heavily chlorinated water running continuously.
And too fast.
And too fast.
Yep.
Yeah. Any pipe.
Yeah.
Any pipe.
Yeah. Here's one. Flow rate. Will's asking a question. If your flow rate's a 40 delta on the heat exchanger, what kind of effect will it have on the secondary loop? We've actually done some classes on this, Will, where we actually show you how to do the math and stuff. But realistically, it's as simple as this. Take the return temperature from your system and add the delta T that you used in sizing the boiler circulator, and you'll have your new set point temperature of the boiler that's required to do that under a design condition. So, I mean, you can do all kinds of math and solve for X and all that stuff that we like to show you, but it's simply that. Okay, so how does it, your question is, how will it affect? It has no ill effect. It just works. It's hydronics and it's hydraulics, and it works good. So.
Very good. Chris Gonzalez asked, Takeo Flow Pro Designer, is it still supported? Well, yes and no. We're not updating it. We're not adding any new features or anything like that to it, but we do have internal support. Brett Zerba at our factory is there for any insider technical support you might have, questions on how to do things or what to do. But as far as updates and additions, we decided to not get out to get out of that part of the business. But it's still a great program. To me, it's a great heat loss program. I never had much luck with it as a system designer because there were just way too many variables. But for a heat loss program, I thought it was absolutely fantastic and very easy to use.
Fast and simple. Yep.
And Bob Dressler says, whole lot of wrong ways to do things, but only a few ways to do them right. That's right. You know it. Absolutely. All righty. What else do we have here? Good night. Going to have dinner. All right. Stanley left us. Let's see what else we have.
Service calls. God bless them.
I'm telling you, that's all right. Boy, look at all these questions. My God, I'm still scrolling down. We're not even close.
Yeah, it's.
Here's one from Bob Dressler again about multiplying by 500 instead of 600. He learned 600. Actually, I've never seen it go that high. Usually, it's the number 500 is usually on the high side.
No, I think he's talking about BTUs per lineal foot on baseboard.
Oh, I'm sorry.
Yeah.
Never mind. Shutting up. Never mind.
No, I'm guessing. I'm not.
I think you might be right. I think you might be right there, Rick.
Yeah.
Rick, Bob, let us know. Are you talking about for sizing baseboard or the universal hydronics formula? That was the 500 jumped into my head, but I'm not normal. But yeah, 600 BTUs per foot is kind of is a lot. You know?
Yeah, it's high, and if you're running 200-degree temperature, well, just go to your baseboard manufacturer, the product you're buying. It'll tell you, at entering air temperature. It'll tell you at an average. Remember, average water
temperature. That's right. It's not supply water temperature. It's average water temperature.
See what it is. So, and hey, we got a plug. Peter's got a plug on a 006E. Yeah, that is the great pump. Understand a 006E for us is giving you a circulator that has, if you were to use a watt as an increment, it's a 41 speed circulator that you could turn way down to 4 watts. And guess what I tell people? Once you burp the pump on high, turn it down to low. You'll be surprised how many jobs that'll do at 4 watts.
Mm-hmm.
So anyway, good plug, Peter. Thanks.
Zach's looking for a Takeo system sizer. No, we don't have a Takeo system sizer. Sorry, Zach.
John, you got one on your wall back there.
You know what? I don't know if I can take this off. Hang on a second here.
Well,
I got to show you.
Okay. But hey, show him and give him a quick story and why we give kudos to B&G for that.
Well, listen, Bell and Gossett, Gil Carlson is really the grandfather of North American hydronics. There's no two ways about it. I mean, he literally wrote the book.
Yeah.
Literally wrote the book. He wrote the seminal paper on the point of no pressure change and pumping away. He wrote all those B&G technical manuals. I mean, this man, they at that time, they were the company of record for commercial hydronics and residential hydronics.
Yeah.
And he invented this. He invented the system sizer wheel. Now, he invented it really just for his own use as a convenience item.
Yeah.
It's a simple way for him to do simple math calculations quickly and easily. And he invented this. He hand drew his own version and created it because he's an engineer and they think like that.
Yeah.
And he kept it in his desk drawer. And he was working with it one day and somebody from the marketing department walked in and said, Gil, what's that? He said, just a little something I whipped up to make doing some math calculations easier for me. And, it's something I use on my own. And he said, can I borrow that for a second? And he took it and went to the marketing department. And the next thing you know, they're cranking these things out by the truckload. And it was just all from Gil's invention. And this is actually not the original. It is a reproduction.
Replica
Of the original system sizer wheel.
Get a lot of glare from your screen, John, but
as you can see, it was there is
nice.
You should see Gil's autograph right there. Okay. Whoa, that's the front of it, and here's the back of it, and it was a I got this as it was called the Carlson Holohan the Carlson Holohan Industry Award of Excellence. I was awarded this in 2012 for, I think they ran out of really good recipients, and I was part of the second wave of, well, let's give it to this guy, you know. But I was awarded this in 2012 for contributions to training. And they quickly regretted that, but they couldn't kick me out because it was like the Supreme Court. It's a lifetime appointment. So, you know, hey, I'm here, right? what are they gonna do? You know, it was kind of like, what was it? Like Rodney Dangerfield going to Bushwood. That's what my tenure with this thing was like. But this is a replica. The original has gone on to subsequent recipients, but it's very special. It's very special.
Very cool.
It's a major award. It's not a leg lamp, but it's a major award.
Yeah.
Oh, and I'm gonna kill myself with this thing before. There we go. Out of the wires. There we go. Put you right back down there. So that's the story of the system sizer wheel. All righty. What else we got? Boy, good questions. Good questions. How do you figure system head? Okay, we're gonna go over that next week. There's easy, there's a little more complicated, but we're definitely going to get into that. We're definitely going to get into that next week. All right. And Dave has joined us. Dave Holdorf is out there.
Yeah, he's been sitting in the wings there. Yeah.
Attaboy, Dave. And you know what, Dave? I got to tell you, we totally forgot. I don't know. Did either of you guys keep track of who would be the winners tonight?
No.
For prizes?
No.
Did you do that, Jim?
What was your criteria for that? Because there was so many great questions from so many different people.
Oh, my criteria is wherever the hell we want.
Okay.
You know what, John? I was wondering why we had so many questions tonight, unusually large numbers. You or Dave, one, must have told them that this week had to do with questions. That's why they're asking so many questions. They want a gift. They want to win the award, and that's why there's so many questions. And
okay,
I didn't keep track. I didn't know I needed to, so I tried to answer them.
Explicit instructions to keep track too, because of our group. Okay, I'm the Mo of our group, of course. You know, Rick is Larry, and well, Jim is Shemp tonight, but Dave is Curly. But Dave is a different kind of Curly, because Dave is the Curly who organizes everything. Okay, he's the organizer of our group.
Kudos to him.
Yeah. You know, if this was Scooby-Doo, okay, he would be Freddy. All right.
Okay.
He's just the guy they let him drive because he's of all the people in Scooby-Doo, he's the only one you'd let drive, right? So he's kind of Freddy from Scooby-Doo. He's Curly from the Stooges. He's the organizer. He keeps us on track. He calls me at least 3 times a day. Did you do this yet? You know, hey, wait a minute. Yes, no, I didn't do that. Oh crap, I'm doing it right now. You know, that kind of thing. So, Dave, you're sitting in a hotel room somewhere. Go through that and pick your winners, because we screwed up on you, babe. I'm sorry to tell you.
What about last week?
We got winners. We had our winners from last week. We awarded them all last week, which was really cool.
Good.
And Patrick S is still out there. How you doing, Patrick? What's the best suggestion for situations? Oh wait, we did that one already. You did that one already, Dave.
Yeah.
Rick, right? Okay, very good. How you doing, Patrick? And you ever want to hear someone talk authoritatively about boiler water treatment, the importance of it, how to do it, how to measure it? There's nobody that I know in the continental U.S., and I'm going to throw Canada in there too, that does it better than Patrick S, man. Patrick, we're gonna have you back in some time for a repeat, because that was I don't want to take, you know, I hate to impose on you, because you know you were so generous with your time, but that was one of the best presentations I've ever sat through. I got to be honest. Boy, look at all these. I'm not running out of these things. My God.
That's what they said. They want the prize. That's why they're doing it. They even admitted it.
Hey, that's fine by me. I don't care why.
Just give everybody a prize and make it easy.
Yeah, there you go. You get a car, and you get a new car, and you get a new car. We don't have new cars to give away, unfortunately. All right. How do you know if a circulator sized correctly? Job site rule of thumb, have you achieved the desired delta T? Yeah, Dan, the only time you're going to achieve the desired delta T is if it's design conditions. That's the thing about delta T. You design 30,000 BTUs, 20-degree delta T times 500. Okay, when do you need 30,000 BTUs? You're designing that for the coldest day of the year, your outdoor design conditions. So you can wait till you're at outdoor design conditions and see where you're at. But you know, the best you can do is the best you can do, right? So you do the math, find your flow rate, find your head loss to the best of your ability, knowing that if you've done an IBR heat loss, a manual J, with use Flow Pro Designer, any one of the million types of software out there to do your heat loss calculations, what are the odds you're going to oversize that? And even if you don't intentionally oversize stuff, right? Say you're doing room dimensions, well, 8.5 feet by 9 3/4 feet. What are you going to call it? 9 by 10, right? 90 square feet. You're going to round up to make the math easy. That's okay. That's normal. All right. Are you exaggerating your outdoor design temperature because you want to be safe, right? Is your outdoor design, Long Island or in Northern Jersey, Jim, what's your outdoor design temperature?
14.
ASHRAE outdoor design temperature.
14.
14 above. What's the local custom?
Well, since the past 10 years of heavy training, I've gotten guys close, but
He's got them turned around.
they did zero
What did it
forever.
used to be?
Yeah, they did zero forever.
Been zero, right?
Yeah.
So you do a heat load in Northern Jersey, it's 0 degrees outside. When the ASHRAE recommended outdoor design temperature is 14, you're overestimating your heat loss by a fair number, right? By a fair number. And you're sizing everything based on that. And then you go through the house and say, well, okay, based on my 0 degree output, my 0 degree outdoor temperature, this room needs 7 feet of baseboard. I'm going to put in 9, or it's 7 feet of baseboard, but it's a 10-foot wall. I'm going to put in 10 feet. Just so I can go from room to room. I don't need any dummy that way, right? You do all these other little things that wind up boom, 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 adding a little bit more and a little bit more as you go along. Even if you do the math, it winds up being bloated, right? So you do all the math to size your circulator, it's going to be too big anyway, right? That's why when we do the flow in head, and let's say my flow in head comes just that much higher than a 007 pump performance curve. Usually you want to be below the curve, right? You want your performance requirement to be below the performance curve. But if I'm just a little bit above that, I'm going to look at it and go, you know what? That's going to be fine. That's going to work just fine because I know I've oversized this thing. I also know 90%, 98% of the heating season, I don't need that requirement anyway. And as long as I got the horsepower in the boiler, even if this was dead on accurate, my flow and head requirement, and my pump is a little bit too small, what's the worst thing that's going to happen? My delta T is going to get just a little bit bigger.
Yeah. No big deal.
Oh, the horror. Oh, the horror.
Yeah. Hey, Ron LaRoque's got one here. He says the last 3 weeks they've been at minus 40. And just saying.
Not in Northern Jersey.
Hey, and that's where Fahrenheit and Celsius meet. He made a note it was minus 40 C, and I said, hey, that's the same as F at that point anyway. And there's a comment by Phil talking about Texas right now. Those poor folks, they're just not used to cold weather, and they're getting hammered big time.
Right.
So,
right.
Yeah, they didn't plan for that probably. So, but
power.
probably not a lot of hydronic heat down in Texas. I don't know.
No, but it's still heat nevertheless.
Yeah. They just have no power, so they got nothing.
They got nothing, right? Generator, hopefully.
It's funny, Johnny asked that question about what's the design temperature. We haven't seen design temperature in this area for probably about 5 years, and now we've had about a month of it.
Yeah. And everybody's going to start going back to 0 now, right?
Yeah.
Well, I actually get emails saying, hey, Jim, hey, look at the temperature. You still believe you're 14? I'm like, yeah, because it didn't go below that yet.
And even if it does, say you do your heat loss to 14 degrees, right? Say you do that heat loss right to Jim's number, 14 degrees outdoor temperature, all right? And you come up with a number of 57,421 BTU heat loss for the house. What are the odds of you A, finding, and B, installing a boiler with an absolute net rated output of 57,421 BTUs and not a BTU more.
No.
You're
Yeah.
slim and none. You're going to pick brand of boiler you like, size up that covers it. Well, what if the brand of boiler you like, size up that covers it, 70,000 BTUs? That's not a badly oversized boiler, and you got 13,000 BTUs sitting in that boiler looking for something to do. They want to get out of town and see the world every once in a while. You're fine. You're fine.
Somebody's got a question about identifying brand name monoflow teas in a system. Just look at the T, and it has some funky stripes on it. If it's so corroded you can't read anything, you can actually feel a stripe on there, and sometimes you can see some flow indication and stuff. Taco has made a tea that's similar to that, and then Bell & Gossett made them, and there's several brands out there. But what you really want to look for is if you see a T in a system that is, hydronic heating system, and it has a T in it, that's a pretty good indication, because most hydronics run in series, not with T's underneath a piece of baseboard. So normally that's an indicator. Hopefully that helps based on that question.
All right, I'm bringing Dave over to the panelist side. Dave, you're now staff, man.
Jump in, Dave.
You're part of the family now. You're part of the family. Can I get the system sizer from our Taco rep? No, you actually have to get it from your B&G rep.
Yeah.
There's nothing we can do about that. It's not our product. This is from Bell & Gossett, and kudos to them. So no, we can't give you these. We don't have them to give you. We don't have them to give you. I wish we did, but we don't. We can tell you the math though. So if you'd rather do the math, we can tell you that.
And somebody points out, Chris saying there's an app for that as well. So you can get electronic version of it just by going to B&G's website and asking for it. So,
that is right. Yes, you can get an app for this. It'll do pretty much everything. Yeah, you're absolutely right. I had that on my last phone. I don't have it on this one. A lot of outdoor tankless with no power and 11 degrees down in Texas. Yeah.
Oh man, it's flooding down in Texas. No, it's freezing down in Texas.
Yeah. Well, did you see that? Video of an apartment building in I think it was in Austin, where I think the sprinkler system froze and burst, and just water was like a river gushing out the front door.
No.
I've never seen anything like it before. Unbelievable. Unbelievable.
Well,
hey guys.
Alrighty. Is that Dave?
It is, yes. I stepped away for a couple minutes.
Dave's not here, man.
Dave. Hey, Dave.
You threw me in as a panelist here, I see.
I did, because we missed you, man. How was the trip? How was the trip to look at colleges?
Not bad today. Not bad. A little snowy, a little cold, but long drive, but all good. All good. How about you guys? How was class tonight?
We enjoyed ourselves. We enjoyed it. Did you get our confession that we kind of completely screwed up the whole prize thing?
No, I did not hear all that. So,
but we're leaving you with the duty to figure it out. Because we don't know what we're doing.
And watch the whole thing.
Yeah, I think you're gonna have to. Yeah. But we will have your prizes, gang. We will have your prizes. I promise you. You just don't know it yet. You'll get an email from Dave. Okay, because Dave is. If you're gonna suck up to anyone in this panel, Dave's the one to suck up to. Ordinarily it would be me, but no, Dave's you want a prize, you just go up to Dave and go, and that's the guy,
Okay, because I got a garage full of stuff.
Yeah, right. I was going to say the easy way, Dave, is just send everybody some. You'll be a hero.
That's easy. Sure, that's easy.
Yeah, and Dave's, hey, I'll approve that expense report.
Hey, he just said it. I heard him. He said it.
There you go.
It's on record. It's being recorded. We got people dropping.
Right. I gotta tell you, I hope you guys enjoyed it. This was a great we're in 2.5 hours now. We're in this 2.5 hours.
Yeah.
This was a great program and just so much fun. I just one of the most fun I've had in a long time. I think it's because we had Shemp with us.
Shemp.
From your good luck charm.
That's it.
Substitute teacher was in.
Yep. I think that's your new nickname, Jim. I'm Jim. We're gonna call you Shemp from now on.
Okay, I'll take it.
Hey, it's better than Curly Joe.
Hey, it's worth repeating. Next week, we're going to dive into 3-speed circulator essentials. Following is ECM essentials. That's about modes and all that. Following that is domestic hot water essentials, the recirc pumps. And then our buddy Dave, who just joined it, is going to wrap things up on St. Patrick's Day with tips and tricks essentials. So.
Yeah, and we've got something special with tips and tricks. Dave, you want to tell the gang the remainders what that tips and tricks is going to be all about?
Definitely. If you guys that are still on, you're the diehard, so that's good. So
yeah.
That means your brain isn't shot just yet from listening. And so the last session of the winter is going to be tips and tricks, but it's not going to be tips and tricks from us four here. Okay, it's going to be from you guys that are out there, and what we want is your best tip, your best tricks to help anybody in the installations or anything that you have out there. We are going to be the jury of those tips that come in, and we're going to present them at the classes. We'll try and get as many as we can to fit in there so we can share amongst ourselves. I mean, what's the purpose of having a group of people like this if you can't share information, right? So so we want to get that information back out. If somebody has found something that's so cool that they've always done it and try to teach their friends, let's try and go the same way and share it to everybody else that we can get to through our Takeover After Dark series. So if your tip or trick makes it to the air, so to speak, you'll be getting a prize pack sent from myself. And then out of the class itself, the best one is going to get voted on by everybody that attends. And the best one is going to get the ultimate prize pack, which starts off with a nice Takeo Yeti cooler filled with goodies on the inside. So that's going to be the grand prize, but everybody that attends gets to vote on that. And that's what's going to make it a lot of fun too.
Hey,
yeah.
Dave, is it a Yeti or an Orca?
Yeti.
Okay. They're both very good units. I saw something that was branded by a Takeo company, and it happened to be an Orca. So
okay.
Anyway,
I got it in the garage the other day.
Nice.
So, yep. I almost didn't want to tell anybody. It looked too nice in my garage.
Hey,
you
not a good time to say anything like that.
All right, very cool, very cool. Well, guys, I think we finally run out. Dan Cook's going to go have dinner. I thought you were going to have some ice cream, Dan.
Ice cream, Dan.
Yeah. But anyway, thank you all. That 73 of you guys are still out there with us. That's just, isn't that incredible?
It's bizarre.
2.5 hours. 2.5 hours, and we could go on another 2.5, but this is the way it is. But we do appreciate
we'll have nothing to talk about next week.
Say what?
We'll have nothing to talk about next week.
Oh no, we'll still play. Between the three of us and four, if Jimmy comes back, we will not run out of stuff to talk about. We will not run out of stuff to talk about. That most definitely. So yeah, diehards, you got that. Absolutely diehard. So hey guys, thank you so much for the gift of your time tonight. Really appreciate it. And as always, if we can't spend time together, this is the next best thing. So it was really a lot of fun. Thank you all, and we'll see you next Wednesday night. And if you guys do Instagram, if you guys are Instagrammers, next Monday at 7 p.m., Dave and I will be having office hours. So stop by and we can chat again on Monday night. We talk about really whatever you guys want to talk about. It's all question and answer and whatever. But that's on Instagram Live, 7 p.m. So for the Takeo Comfort Solutions Instagram page, we'll be running that.
So make sure you need to be following the Takeo page, not myself, not John. You want to get to the Takeo page. Make sure you're following that, so this way you get the notice on your device that we've gone live. It's going to be 7 o'clock Eastern, and we like to call it office hours because just imagine walking down the hallway and you see the office door open and the two of us are sitting in there, and you just got a cup of coffee in your hand and you just lean up against the doorway and just decide to have a conversation. So so that's what we consider office hours. Normally, yes, office hours are from 9 to 5, but we know you guys are out there fixing the heat, keeping the heat on for people. So that's the next best thing we got for you, rather than during the daytime when you guys are out there fixing stuff. So stop on by, come see us on Monday night. We'll continue
before we go,
basically the same thing here.
Yeah, there we go. Hey, before we go, big round of applause for Jim DePalma.
Thank you. It's an honor. Thank you very much. You guys are my mentors, so I learn from you all the time. Thank you. Thank you.
Hey, our pleasure, and it's always a joy to hang with you, Jim. I wish we could do it in person. That's all.
Does he get substitute pay or hazard pay tonight?
He didn't have to pay us at all. It was we didn't charge him. So.
Freebie.
All righty, folks. Hey,
so long,
night, everybody. Have a great week.
Keep
Stay
it together.
Enjoy, y'all.
There you go.